Hello there, and welcome to Life Beyond Seen, a quiet place where big ideas are allowed to slow down, where curiosity doesn't rush, and where science takes a gentler path through the dark, often arriving not with answers, but with a sense of wonder that feels comfortable enough to rest beside. Tonight, we're drifting into a story that feels almost impossible on first encounter. A story about something so large that even the rules of nature seem to hesitate around it. Something that by many measures should not exist at all. And yet, it does. It moves through the ocean right now, as calmly as if there were never any doubt. The blue whale is not just the largest animal alive today. It is the largest animal that has ever lived. Larger than any dinosaur that ever walked. Larger than anything that crawled, flew, or thundered across land in the long history of this planet. When people hear that fact, it often slides past without fully landing like a number too big to picture. Largest ever can sound abstract, almost ceremonial. But when you slow down and actually look at what that means, the scale becomes unsettling in a quiet way. A single tongue that can outweigh an elephant. A heart so large that a child could crawl through its arteries. A body so massive that if it were laid out on land, gravity itself would begin to protest. And that's where tonight's question begins. Not how big blue whales are, but why they're allowed to be big at all. Why physics didn't step in and say no. Why biology didn't quietly impose a ceiling. Why evolution didn't stop long before reaching something so extreme. When you look closely at the constraints that govern life on Earth, bones, muscles, lungs, blood, energy, heat, gravity, it becomes clear that size is not just a matter of growing larger. It is a negotiation, a series of limits that press harder and harder the bigger you become. Somewhere along that negotiation, most creatures are forced to stop. Their skeletons would buckle, their hearts would struggle, their lungs could no longer deliver oxygen fast enough, their food intake would become impossible to sustain. For life on land, these limits arrive quickly and decisively. That's why elephants sit near the upper boundary of what terrestrial life can manage. Even they live carefully balanced lives, conserving energy, avoiding unnecessary strain, existing close to the edge of what their bodies can support. But blue whales didn't just approach that edge. They crossed it by an astonishing margin. They became so large that, on paper, they seem like a mistake. An error that slipped through the checks and balances of nature. A creature that breaks the quiet assumptions we tend to carry about what life can do. So tonight, we're not rushing to marvel. We're slowing down to understand. To sit with the question of why blue whales shouldn't exist. And how, somehow, they do anyway. Because this isn't a story about size for its own sake. It's a story about physics quietly bending without breaking. About an environment that rewrites the rules just enough to allow the impossible. About a lineage that found a loophole so specific and so rare that it has only happened once. As you listen, notice where you are right now. The room around you. The weight of your body where it rests. The pace of your breathing. Somewhere far away beneath layers of moving water, an animal the length of a city bus is breathing too, lifting its body to the surface, releasing a column of air that looks almost gentle compared to the mass beneath it. Two lives operating under the same laws of nature, but at scales so different, they might as well belong to different worlds. And just out of curiosity, where are you listening from right now? Not in a logistical sense, but in a quieter one. A bedroom, perhaps, or a dimly lit room where the day has finally loosened its grip. Maybe you're winding down, or maybe you're simply letting your mind wander somewhere slower. Whatever brought you here, you're very welcome. If you find this space calming, or if you enjoy these slow journeys through questions that don't demand urgency, you're always invited to like the video or subscribe. It helps this corner of quiet reach others who might need a place where curiosity doesn't shout. No pressure, just an open door. Now, before we move deeper, it helps to set aside a common way of thinking about size. We tend to imagine that bigger is just more. More cells, more weight, more volume. But biology doesn't scale cleanly. Double the size of an animal and you don't simply double the demands placed on its body. You multiply them. Mass increases faster than strength. Volume grows faster than surface area. Heat becomes harder to release. Oxygen becomes harder to deliver. Signals take longer to travel. Every advantage of size arrives bundled with new problems, and those problems grow faster than the solutions. This is why extreme size is rare. Why evolution usually settles for good enough rather than pushing toward maximum. Most environments punish excess. They reward efficiency, adaptability, and balance. So the fact that something as enormous as a blue whale exists at all suggests that something unusual is happening. That somewhere, the environment itself is carrying part of the load. The ocean, as it turns out, is not just a backdrop. It is an accomplice. Water changes everything. It lifts weight. It softens gravity. It allows bodies to grow larger without collapsing under their own mass. But even that explanation is only the beginning. Because water alone doesn't solve the problem of feeding something so large, or supplying it with oxygen, or keeping its tissues alive over decades, or allowing it to move with anything resembling grace. To understand how blue whales cross this threshold, we have to move carefully through a chain of constraints. We have to look at the physics of support, the biology of circulation, the economics of energy, and the slow, patient-shaping force of evolution working over millions of years. We have to understand why land never stood a chance, and why even the ocean only barely does. And as we move forward, keep in mind that this story is not about inevitability. Blue whales were not destined to exist. Their presence is not the natural endpoint of size increasing over time. It is the result of a very specific alignment of conditions, resources, and opportunities. Change any one of them, and the story collapses. So as we ease into what comes next, hold on to this idea. The blue whale is not powerful because it is large. It is large because, for a brief window in Earth's history, being large finally made sense. When people hear the phrase, the largest thing that ever lived, it often lands as a curiosity rather than a reality. It sounds impressive in the same way record numbers sound impressive. Bigger than this, heavier than that, longer than something else. The mind acknowledges it, nods politely and moves on. But the blue whale resists that kind of casual understanding. Its size is not just large, it is disorienting. It forces comparisons to fail and intuition to break down. To really meet it, even in imagination, requires slowing the pace and letting the scale unfold piece by piece. An adult blue whale can reach lengths of around 30 meters, sometimes more. That number alone does not say much. 30 meters is abstract until you place it against something familiar. That is longer than a typical city bus. Longer than many apartment buildings are wide. If you were standing at one end of a blue whale lying straight, the other end would be far enough away that details would begin to soften. You would not take it in all at once. Your eyes would move along it in sections, the way they do when looking at a long bridge or a freight train passing by. And length is only the beginning. Weight is where the story becomes harder to hold on to. A fully grown blue whale can weigh over 150 metric tons. Some estimates push higher. That is the mass of more than 30 large elephants combined into one living body. Not stacked, not clustered, unified. Held together by bone, muscle, connective tissue, blood and skin, all working continuously to keep that mass alive. What makes this harder to grasp is that we rarely encounter weight in this way. We see heavy things as static. Buildings, ships, mountains, things that sit still or move slowly with mechanical assistance. A blue whale, by contrast, is not a structure. It is not braced by steel or concrete. It is a moving organism. It accelerates, it turns, it dives, it rises, it propels itself through water using muscle alone. That alone should feel strange. Then there is the volume, the sheer amount of space a blue whale occupies. Its body is not narrow or compressed. It is broad and deep, with a chest cavity large enough to hold multiple humans standing upright. Inside that space are lungs that can exchange enormous volumes of air, a heart that weighs as much as a small car, and a circulatory system that has to push blood across distances that would challenge any pump. Even individual parts of the blue whale defy scale. Its tongue alone can weigh several tons. Its arteries are so wide that, at least in theory, a human could crawl through them. Its flukes span wider than many rooms. Its skin can be more than 30 centimeters thick in places, layered with fat that serves as insulation, energy storage and buoyancy control all at once. And yet, despite all this, the blue whale is not dense in the way we might expect. Much of its mass is distributed through tissues designed to interact with water. Blubber is not just padding. It is a carefully evolved material that stores energy without adding rigidity. Muscle fibers are arranged to generate slow, powerful contractions rather than rapid bursts. Bones are strong but not excessively heavy, avoiding unnecessary mass that would increase the burden of movement. When people imagine a creature this large, they often picture something lumbering and awkward, a slow-moving giant constantly straining under its own weight. But meeting the blue whale in reality, or even through careful observation, challenges that assumption. In the water, it moves with a kind of deliberate ease, not fast in the way smaller animals dart, but smooth, controlled, and surprisingly efficient. Part of this impression comes from how quiet blue whales are at the surface. When one exhales, the sound is not explosive. It is more like a deep, steady release, followed by a brief pause before the body slips back beneath the water. There is no sense of effort, no visible struggle. The animal appears composed, almost indifferent to its own size. This calm exterior hides an extraordinary level of internal coordination. Every movement involves managing enormous forces. When a blue whale beats its tail, it is pushing against thousands of kilograms of water. The muscles responsible for this motion must generate immense power while avoiding fatigue. The skeleton must transmit that force without cracking. The joints must handle repeated stress over decades. Then there is the simple fact of time. Blue whales can live for 70 to 90 years, possibly longer. This means their bodies must not only function at extreme scale, but continue functioning for decades without catastrophic failure. Wear and tear that might cripple a smaller animal becomes a serious threat when multiplied across such size and lifespan. Yet blue whales persist. To really meet the blue whale as the largest thing that ever lived, it helps to compare it not just to other animals, but to the absolute limits we know. Dinosaurs, often invoked as the benchmark of prehistoric size, do not surpass it. Even the largest sauropods, with their long necks and massive bodies, likely weighed less than the biggest blue whales. They carried their mass on land, under gravity's full force, constrained by the strength of bone and muscle alone. The blue whale's dominance in size is not a marginal victory. It is decisive. Nothing else in the fossil record approaches its combination of length and mass. It occupies a category of its own, separated by a gap so large that it feels less like a winner of an evolutionary contest and more like an anomaly. This raises an immediate question. If being large offers advantages, why did nothing else reach this size? Why only one lineage in one environment during a relatively narrow window of Earth's history? The answer is not that evolution lacked imagination. It is that the constraints are severe, and most attempts would have failed. Meeting the blue whale means confronting those constraints directly. Gravity, for example, is relentless. On land, it compresses tissues, strains joints, and limits how tall or heavy a body can be before it collapses. Even in water, where buoyancy offsets much of this force, gravity still matters. The internal structure of the animal must support itself when surfacing, when turning, when accelerating. Then there is oxygen. A body this large consumes enormous amounts of it, yet cannot breathe continuously. Blue whales are air-breathing mammals. They must surface, inhale, and then rely on stored oxygen while diving. Their lungs, blood, and muscles must work together to store and distribute oxygen with extraordinary efficiency. A failure here would be fatal. Heat is another challenge. Large bodies generate and retain heat. In warm environments, this can become dangerous. Blue whales solve this partly by living in cold oceans, and partly through the sheer surface area of their bodies interacting with water, which absorbs heat far more effectively than air. Even so, their thermal balance is delicate. And food, perhaps the most obvious constraint. A blue whale eats tiny prey, krill, small crustaceans only a few centimeters long. To sustain its mass, it must consume several tons of krill each day during feeding seasons. This requires not just abundant food, but food concentrated in a way that makes harvesting it efficient. Without dense swarms of krill, the entire system would collapse. All of this begins to hint at why meeting the largest thing that ever lived is not just an encounter with size, but with improbability. The blue whale exists at the intersection of many favourable conditions: oceanic buoyancy, cold water, abundant prey, efficient feeding strategies, slow metabolism relative to size, long evolutionary time. But even knowing this, it is difficult to shake the sense that something here is excessive, that the animal is skating close to the edge of what is possible, and in many ways it is. Blue whales do not have much room to grow larger. They're already pushing against limits imposed by physics and biology. Any significant increase in size would demand changes that may not be achievable. This makes encountering the blue whale feel less like observing a triumph and more like witnessing a balancing act that somehow holds. A living demonstration of how far the rules can be stretched without breaking. And that feeling only grows stronger when you consider how fragile this existence actually is. Despite their size, blue whales are not invulnerable. Their populations were devastated by industrial whaling in the 20th century. Machines and explosives proved far more dangerous than any natural predator. Even now, ship strikes, noise pollution and changes in ocean ecosystems pose serious threats. The largest thing that ever lived is, in many ways, still precarious. This fragility adds another layer to meeting the blue whale. Size does not equal dominance in the way we often assume. It does not grant immunity. It does not guarantee survival. Instead, it creates dependence. Dependence on stable ecosystems, predictable food supplies, and vast open spaces. As we hold all this together, the image of the blue whale begins to shift. It is no longer just a marvel of scale. It becomes a question mark. How did something so constrained manage to exist at all? What had to align, and what had to give way for this to happen? To answer that, we have to step back from the whale itself and look at the pressures acting against it. We have to understand why size at a certain point stops being an advantage and starts becoming a liability. Why most lineages turn away long before reaching this extreme. Why growth is not just a matter of adding more tissue, but of renegotiating the fundamental forces that shape living bodies. Meeting the largest thing that ever lived is only the beginning. The real story lies in understanding why becoming that large is usually a bad idea, and why, in this one remarkable case, it worked just well enough. At first glance, getting bigger seems like a straightforward advantage. Larger animals are harder to intimidate. They can travel farther on the same amount of energy. They lose heat more slowly. They are often safer from predators simply because very few things are capable of attacking them. From a distance, size looks like a winning strategy, and in many cases it is. Evolution has returned to it again and again, producing larger bodies whenever conditions allow. But this logic only holds for a while. Past a certain point, size stops behaving like a benefit and starts acting like a problem that must be managed constantly. The same features that once offered advantages begin to generate new pressures, and those pressures do not increase gently. They stack, they compound, they accelerate. One of the first issues to appear is simple structural stress. Every body is built from materials with limits. Bone can only withstand so much compression before it fractures. Muscle fibers can only generate so much force relative to their thickness. Tendons and ligaments can only absorb so much strain before tearing. As an animal grows larger, its mass increases faster than the strength of its supporting structures. This is not a design flaw, it is geometry. When you double an animal's length, you do not double its weight. You increase it many times over. Volume grows with the cube of size, while cross-sectional strength grows much more slowly. This means that a body scaled up without changes would collapse under its own weight. Evolution responds by thickening bones, widening joints, reinforcing connective tissue. But each of these fixes adds mass, which adds more stress, which requires further reinforcement. It becomes a feedback loop. On land, this problem is especially unforgiving. Gravity applies its force constantly and evenly. There is no relief. Every step places enormous strain on joints. Every movement requires lifting and stabilizing large amounts of weight. Even standing still demands continuous muscular effort to prevent collapse. This is why large land animals tend to move carefully, avoid jumping, and spend much of their time resting. The margin for error is thin. Beyond structure, there is circulation. As bodies grow larger, the distance blood must travel increases. Oxygen and nutrients must be delivered to tissues farther from the heart. Waste products must be carried away just as efficiently. To do this, the heart must pump harder, vessels must be stronger, and blood pressure must be carefully regulated. But higher pressure increases the risk of damage to vessel walls. Thicker vessels reduce efficiency. Larger hearts require more energy to run. At small scales, diffusion helps. Oxygen can move short distances through tissues without much assistance. At large scales, diffusion becomes too slow. Everything must be actively transported. This introduces delays. Signals take longer to travel. Responses slow down. Coordination becomes more difficult. Then there is heat. Metabolism generates warmth. In small animals, this heat escapes easily because surface area is large relative to volume. In large animals, heat builds up. This can be helpful in cold environments, but dangerous in warm ones. Excess heat must be shed somehow. Sweating, panting, increased blood flow to the skin all help, but they require water and energy. At extreme size, managing heat becomes a constant challenge. Feeding adds another layer. Bigger bodies need more energy, but not in a simple linear way. A large animal does not just eat more, it must eat more efficiently. Food must be abundant, accessible, and easy to process. If food is scattered, scarce, or slow to digest, the energy costs of foraging can exceed the energy gained. At that point, size becomes a liability. This is why many of the largest animals on land are herbivores. Plants are abundant but low in energy density. To survive on them, animals grow large digestive systems and spend much of their time eating. Even then, there is a ceiling. Past a certain size, eating enough becomes impractical. There are only so many hours in a day and digestion can only move so fast. Predation, often cited as a benefit of size, also changes character at large scales. While large animals have fewer predators, they are not free from danger. Injuries that would be minor for a small animal can be catastrophic for a large one. A broken limb, an infection, or internal damage may not heal effectively. Recovery is slow. Medical mistakes, in evolutionary terms, are costly. Reproduction introduces yet another constraint. Large bodies take longer to grow. Gestation periods are longer. Offspring are fewer and more energetically expensive. This slows population recovery and makes species more vulnerable to environmental changes. When conditions worsen, large animals cannot adapt quickly by producing many offspring. They must endure. All of these factors converge to create a zone where size becomes more trouble than it is worth. Evolution does not aim for maximum size, it aims for survivable balance. If a trait increases risk without sufficient payoff, it tends to be pruned away over time. This is why extreme size is rare. It is not because life lacks ambition, it is because the costs escalate faster than the benefits. Most lineages explore size up to a point, then stabilize or reverse. They find a workable scale and stay there. What makes this especially interesting is that these problems do not announce themselves loudly. There is no single moment where size suddenly becomes bad. Instead, constraints accumulate quietly. Slightly more stress on joints, slightly longer recovery times, slightly greater dependence on stable food supplies. Over generations, these small disadvantages add up. The environment plays a decisive role in where this tipping point lies. On land, gravity and temperature push it downward. In water, buoyancy softens some of these constraints. Weight is partially supported, movement requires less lifting and more pushing. Heat exchange is more efficient. This shifts the balance. But even in water, the problems do not disappear. They change shape. Drag increases with size. Turning becomes slower. Oxygen must still be obtained from air. Feeding still depends on ecological conditions. The ocean does not eliminate limits, it rearranges them. When size becomes a problem, it is rarely because one system fails outright. It is because many systems operate closer to their limits at the same time. The heart works harder. Bones experience greater loads. Energy margins shrink. Flexibility decreases. There is less room for error. This is why evolution tends to avoid the edge. Living close to physical limits is risky. A small change in environment, climate or food availability can push a species over the brink. Stability favours moderation, which makes the existence of the blue whale feel even stranger. Because it does not just approach these limits, it lives among them. Its body operates near thresholds that most organisms never encounter, and it does so not briefly, but for decades. Understanding when size becomes a problem helps explain why blue whales are not just big animals, but exceptional ones. They are not simply scaled-up versions of smaller whales. They represent a different solution entirely, one that depends on a specific set of conditions being met simultaneously. As we move forward, the question becomes sharper. What exactly are the forces that normally stop growth? Which ones are softened by water, and which remain stubbornly in place? And how did this one lineage manage to negotiate with gravity, energy and biology just well enough to keep going? Because the problems of size do not go away, they wait. And understanding how blue whales live with them means looking directly at the forces pushing back hardest. Gravity does not argue loudly. It does not announce itself as a barrier or issue warnings when limits are approached. It simply applies the same force, relentlessly, to everything with mass. Small bodies barely notice it. Large bodies live under its constant pressure. And when size increases far enough, gravity becomes less of a background condition and more of an active participant, quietly objecting to every extra kilogram that is added. For most animals, gravity is something their bodies are designed around so thoroughly that it fades into the background of daily life. Muscles contract, bones hold, joints align, and movement happens without conscious thought. The system works because the scale is manageable. The forces involved remain well within what tissues can tolerate. But as size increases, gravity's influence grows disproportionately, and the body must spend more and more of its resources simply resisting collapse. On land, this resistance is obvious. Every step involves lifting mass against gravity. Every pause involves stabilizing it. The skeleton acts as a load-bearing framework, and the muscles act as dynamic supports, constantly adjusting tension to maintain posture. At small and moderate sizes, this arrangement is efficient. At large sizes, it becomes precarious. The problem is not just weight, it is stress. Stress is force divided by area. As animals grow larger, the force generated by their weight increases faster than the area of their bones and joints, unless those structures are reinforced. Evolution responds by thickening bones and widening joints, but this adds mass, which adds more force, which requires further reinforcement. The cycle continues until it becomes inefficient or unsustainable. There is also the issue of failure modes. Small animals can fall, trip, or collide without serious injury. Large animals cannot. A fall that would be trivial for a small creature can be fatal for a large one. The energy involved in the impact scales with mass. Fractures become catastrophic. Internal organs experience shear forces that can cause damage even without external signs. This is why large land animals move carefully. They avoid sharp turns. They rarely jump. They prefer stable terrain. Their behaviour reflects an awareness, built into their nervous systems, that gravity is unforgiving at their scale. Caution becomes part of survival. Now imagine pushing this system much further. Imagine adding tens of tons of mass. Imagine joints supporting loads far beyond what bone can comfortably manage. Imagine muscles that must contract continuously just to prevent collapse. This is the situation blue whales would face if they lived on land. It is not that they would be clumsy or slow. They would be structurally compromised. Their own weight would become a constant threat. This is why stranded whales struggle so dramatically. When a blue whale beaches itself, gravity reasserts full control. The buoyant support of water disappears, and the animal's body is suddenly subjected to forces it was never designed to handle. Internal organs compress. Blood flow is disrupted. The ribcage deforms under its own mass. Even with immediate intervention, survival is unlikely. The animal is not adapted to exist without water's support. Water changes gravity's role, but it does not eliminate it. Buoyancy counteracts much of an object's weight, effectively reducing the load that structures must bear. In water, a body displaces a volume of fluid equal to its own volume. The upward force from that displaced water offsets a large portion of gravitational pull. For a blue whale, this is the difference between functional movement and structural failure. This buoyant support allows bones to be lighter than they would need to be on land. It allows joints to experience less compressive stress. It allows muscles to focus on propulsion rather than constant support. In effect, the ocean shares the burden. Gravity still acts, but its objection is softened. However, buoyancy introduces its own complexities. Support is not uniform, it depends on orientation, movement, and water density. When a whale turns, accelerates, or surfaces, gravity's influence shifts. The body must handle changing stress patterns. The skeleton must be strong enough to manage these variations without overbuilding, which would add unnecessary mass. There is also drag. While water reduces the burden of weight, it resists motion. Drag increases with surface area and speed. A larger body experiences more resistance as it moves through water. This means that while gravity is less oppressive, energy demands for movement increase. The whale must generate enough force to overcome drag while maintaining structural integrity. Still, compared to land, the ocean offers a rare compromise. Gravity is present, but negotiable. Weight becomes something that can be distributed, rather than something that must be carried entirely by internal structures. This is one of the key reasons extreme size is possible in aquatic environments but not terrestrial ones. Yet even in water, gravity imposes limits. The blue whale's skeleton must still support the body when partially out of water. Surfacing to breathe exposes parts of the body to full gravitational load. The ribcage, spine, and muscles must withstand this repeatedly over decades. Any weakness would be amplified over time. Gravity also affects circulation. Blood must be pumped vertically through the body. Differences in pressure arise between tissues at different depths. On land, these differences are modest. In a body as long as a blue whale's, they become significant. The heart must generate enough pressure to move blood upward without damaging vessels. Valves and vessel walls must be adapted to manage this gradient. Then there is the matter of movement coordination. Large bodies have more inertia. Starting and stopping motion requires more force. Gravity resists sudden changes in direction. The nervous system must anticipate movements and adjust muscle activation in advance. This reduces agility and increases the cost of mistakes. All of this points to a central truth. Gravity does not forbid size outright. It makes size expensive. Every additional increase in mass comes with hidden costs that must be paid continuously. For most organisms, the balance tips long before reaching extreme scales. The blue whale exists because it found a way to live where gravity's objections are muted, not silenced, but reduced enough to manage. The ocean provides support, but the whale's body must still be carefully engineered to cooperate with that support. Nothing about this arrangement is casual. This also explains why size increases in whales did not happen all at once. Fossil evidence suggests a gradual trend toward larger bodies, coinciding with changes in ocean productivity and feeding strategies. As conditions allowed more efficient feeding, larger size became viable, but each step required adaptations to keep gravity's pressures in check. Importantly, this path is narrow. It depends on stable water density, predictable buoyancy, and an environment that allows the animal to spend nearly all its time supported. Remove any of these factors, and gravity's quiet objection becomes overwhelming. This is why blue whales cannot retreat to shallower waters permanently. It is why they cannot survive prolonged periods out of water. It is why their entire existence is tied to the open ocean. Their size is not portable. It only works in a specific context. Gravity in this story is not an enemy. It is a constant auditor, checking every design choice, every movement, every increase in scale. The blue whale passes this audit not by overpowering gravity, but by working around it, by letting water absorb what gravity demands. Understanding this makes the blue whale feel less like a triumph of strength and more like a triumph of balance. A body so large that it would fail under normal conditions, yet tuned precisely to an environment that keeps failure just out of reach. And as we continue, it becomes clear that gravity is only one of the objections that size must answer. Even when weight is partially lifted away, the internal demands of living tissue remain. Muscles must still contract, bones must still resist stress, blood must still circulate, energy must still be supplied. Gravity sets the stage, but it does not act alone. The next pressures emerge from within the body itself, from the materials that make up living structure and the limits they impose when pushed to extremes. Even with gravity softened by water, a body as large as a blue whale cannot escape the basic limitations of the materials it is made from. Living tissue is remarkable, but it is not infinitely adaptable. Bone, muscle, and blood each come with physical constraints that do not disappear just because an animal grows larger. In fact, at extreme scales, those constraints become more pronounced, forcing careful compromises in how the body is built and how it functions. Bone is often imagined as rigid and unyielding, a solid framework that simply holds everything up. In reality, bone is a living tissue that balances strength with flexibility. It must be strong enough to resist bending and compression, yet flexible enough to absorb shocks without snapping. At small sizes, this balance is relatively easy to maintain. At large sizes, it becomes increasingly delicate. As an animal grows, its bones must thicken to support additional mass. But thickening bone is not free. Bone is heavy. Adding more of it increases the load that must be supported elsewhere in the body. It also changes how forces travel through the skeleton. Stress concentrates at joints and connection points, which then require further reinforcement. This cascading effect places a practical ceiling on how much bone can be added before it becomes counterproductive. Blue whale bones reflect this compromise. They are massive, but not proportionally massive compared to the animal's size. They rely on the buoyant support of water to carry much of the load that bone would otherwise need to bear. This allows the skeleton to be lighter than it would need to be on land, but it also means the bones are not designed to support the body without that external assistance. The skeleton works because the environment completes the structure. Muscle introduces a different set of limitations. Muscle strength increases with cross-sectional area, while the mass it must move increases with volume. This means that simply scaling up muscle size does not keep pace with the demands of a larger body. At some point, muscles become insufficient to move the mass they are attached to, unless their arrangement changes. Blue whale muscles are not built for rapid, precise movements. They are built for slow, powerful contractions that can move large volumes of water with minimal wasted energy. The tail muscles in particular are enormous, arranged to generate thrust efficiently over long periods rather than short bursts. This design sacrifices agility for endurance and efficiency. But even this approach has limits. Muscles require oxygen to function. The larger the muscle mass, the greater the demand for oxygen. This demand must be met through the circulatory system, which brings us to blood. Blood is the transport medium that keeps tissues alive. It carries oxygen from the lungs to the muscles and organs, delivers nutrients, removes waste, and helps regulate temperature. In a very large body, the distances involved are extreme. Blood must travel meters rather than centimeters. Delays that would be insignificant in a small animal become meaningful in a large one. The heart must generate enough pressure to push blood through this vast network without causing damage. Too little pressure, and tissues are starved of oxygen. Too much, and vessels risk rupture. Vessel walls must be strong yet flexible. Valves must prevent backflow. The entire system must remain stable over decades of continuous use. The blue whale's heart is proportionally large, but again, not large enough to brute force the problem. Instead, the circulatory system relies on a combination of slow heart rates, large blood volumes, and elastic vessels to maintain flow efficiently. At rest, a blue whale's heart may beat only a few times per minute. Each beat moves a tremendous volume of blood. This slow rhythm reduces wear on the heart and vessels, but it also means the system has limited capacity for rapid adjustment. Blue whales cannot suddenly increase activity levels without consequence. Their physiology favours steady, predictable patterns. Sudden exertion would strain the system. Oxygen storage is another critical factor. Because blue whales are air-breathing mammals, they must store oxygen while diving. Much of this oxygen is stored not in the lungs, but in the blood and muscles themselves. Specialised proteins bind oxygen and release it gradually during dives. This system works well, but it's finely tuned. Exceed its capacity, and tissues begin to suffer. Blood volume also contributes to thermal regulation. Warm blood can distribute heat throughout the body, but shedding excess heat is harder at large scales. Blood flow to the skin and extremities must be carefully controlled to avoid overheating or excessive heat loss. This balancing act becomes more complex as body size increases. The limits of bone, muscle, and blood are not independent, they interact. Heavier bones demand stronger muscles. Stronger muscles demand more oxygen. More oxygen demands greater blood flow. Greater blood flow demands stronger vessels and a more powerful heart. Each solution amplifies the demands on the next system. This interconnectedness is what makes extreme size so difficult to achieve. You cannot simply improve one component. The entire system must be rebalanced. Evolution works slowly, modifying one feature at a time, constrained by what already exists. Reaching the scale of a blue whale required not just growth, but a reorganization of how tissues cooperate. There are also repair and maintenance costs to consider. Living tissues are constantly damaged and repaired. Microfractures form in bone. Muscle fibers tear and rebuild. Blood vessels experience wear. In a very large body, repair takes longer. Damage accumulates over greater distances. The risk of failure increases with time. This makes longevity at large size especially challenging. Blue whales live long lives, which means their tissues must withstand repeated stress cycles for decades. Their bodies are built not for peak performance, but for durability. Everything is designed to operate well below maximum capacity most of the time. Even with all these adaptations, the system operates close to its limits. There is little redundancy, little excess capacity. This is one reason why injuries and illnesses can be so devastating. A compromised muscle, a damaged vessel, or a disruption in circulation can have consequences that ripple through the entire body. This also helps explain why blue whales did not evolve on land and could not return there. The limits of bone, muscle, and blood would be exceeded almost immediately. Without buoyancy, bones would need to be thicker, muscles stronger, blood pressure higher. The cost of these changes would cascade until the system failed. In water, the balance holds, just barely. The environment absorbs part of the burden, allowing tissues to operate within their tolerances, but even there, the whale's body must be constantly managed. Movement patterns are conservative, energy expenditure is controlled, behaviour aligns with physiology. Understanding these limits makes it clear that the blue whale is not simply large by chance. It is large because every system in its body has been shaped to stretch as far as possible without tearing. There is no single breakthrough. There is no one feature that explains its size. It is the cumulative result of many small accommodations, each one preventing collapse. As we move forward, it becomes evident that even with bones that hold, muscles that move, and blood that flows, there remains another fundamental challenge. A body this large must interact with the outside world in specific ways to sustain itself. It must breathe. It must feed. And those processes introduce constraints just as strict as any internal limit. Because no matter how well a body is built, it still has to exchange matter and energy with its environment. And at extreme scale, even that simple requirement becomes complicated. Breathing is so automatic for most animals that it rarely feels like a limitation. Air moves in and out. Oxygen enters the bloodstream, carbon dioxide leaves. The process repeats quietly, thousands of times a day, without drawing attention to itself. At small and moderate scales, breathing is rarely a bottleneck. It keeps pace with demand. It adjusts quickly. It fades into the background of life. At the scale of a blue whale, breathing becomes something else entirely. It becomes a logistical challenge, a negotiation between physics, anatomy, and time. A process that operates close to its upper limits every time the animal dives, surfaces, or exerts itself. Breathing does not fail in blue whales, but it does not have much room to spare. The first complication is that blue whales are mammals. They breathe air, not water. This immediately separates them from fish and other aquatic organisms that can extract oxygen continuously from their surroundings. Every breath a blue whale takes must be gathered at the surface, compressed into the lungs, stored in the body, and then carefully rationed while underwater. This would be manageable if the whale were small, but at extreme size, oxygen demand rises sharply. Muscles consume oxygen. Organs consume oxygen. The brain, though proportionally small, still requires a steady supply. And unlike many smaller diving animals, blue whales cannot rely on rapid breathing cycles to compensate. They cannot breathe frequently while active underwater. They must plan. The lungs of a blue whale are enormous. In absolute terms, they can hold thousands of litres of air. But relative to body mass, lung capacity does not scale as generously as one might expect. Lung volume increases with size, but so does oxygen demand, and not at the same rate. Simply having larger lungs does not solve the problem. To make matters more complex, blue whale lungs are not used the same way human lungs are. When a whale dives, the pressure of the water compresses the chest cavity. The lungs collapse safely, pushing air out of the smallest airways and preventing nitrogen from dissolving into the blood at dangerous levels. This protects the whale from decompression sickness, but it also means the lungs are not the primary oxygen reservoir during a dive. Instead, most of the oxygen is stored in the blood and muscles. Blue whales have extremely high blood volumes, and their blood is rich in hemoglobin, the protein that binds oxygen. Their muscles contain large amounts of myoglobin, another oxygen-binding protein that allows muscle tissue to store oxygen directly. This arrangement allows the whale to continue functioning even when the lungs are effectively offline. This system works, but it is not infinite. Oxygen stores are finite. Every movement consumes them. The larger the body, the faster those stores are depleted during exertion. This places a hard limit on how active a blue whale can be while submerged and for how long. This is one reason why blue whales move the way they do. Their swimming is steady and deliberate. Rapid bursts of speed are rare and costly. Even feeding, which might appear passive, involves significant effort. Lunging through dense swarms of krill requires opening the mouth wide, expanding the throat pleats, and accelerating a massive body through water. This consumes oxygen rapidly. When oxygen runs low, the whale must surface. Surfacing itself is not free. It requires lifting part of the body against gravity and breaking the surface tension of the water. Once at the surface, the whale must replenish its oxygen stores quickly and efficiently. Blue whales accomplish this with remarkable speed. A single breath can exchange a large percentage of the air in the lungs. Unlike humans, who exchange only a fraction of lung air with each breath, whales inhale and exhale deeply. This allows them to take in large amounts of oxygen in a short time. Even so, breathing remains a pacing factor. The whales' dive patterns, feeding strategies, and migration routes are all shaped by the need to balance oxygen supply and demand. There is little flexibility. Extended exertion without recovery would lead to oxygen debt, forcing the whale to rest or risk tissue damage. The timing of breathing also matters. Blue whales cannot simply surface whenever oxygen runs low. They must coordinate surfacing with their position, depth, and surroundings. Surfacing in rough seas, near ice, or in shallow waters carries risks. This adds another layer of constraint to their behaviour. There is also the matter of carbon dioxide. As oxygen is consumed, carbon dioxide accumulates. Elevated carbon dioxide levels can disrupt blood chemistry and interfere with muscle function. Efficient removal of carbon dioxide is just as important as oxygen uptake. The whale's breathing must restore balance quickly to allow continued activity. Temperature regulation intersects with breathing as well. Exhaled air carries heat away from the body. In cold environments, this heat loss must be managed. Blue whales rely on their thick blubber to retain warmth, but excessive heat loss through respiration still matters, especially during repeated surfacing. Another challenge arises from sheer distance. Oxygen must travel from the lungs to tissues located meters away. Even with efficient circulation, delays occur. This means that oxygen delivery cannot respond instantly to sudden changes in demand. The system favours predictability over spontaneity. This is why blue whales do not sprint unpredictably or engage in prolonged chases. Their physiology does not support it. They are not built for quick reactions or sustained high-speed pursuits. Their feeding strategy relies instead on encountering dense prey concentrations, where a few large feeding events provide sufficient energy without constant exertion. Breathing also interacts with sound production. Blue whales produce some of the loudest vocalizations of any animal. These sounds are generated without expelling air in the way human speech does, but the structures involved still interact with the respiratory system. Sound production requires precise control of airflow and pressure, adding another demand on already complex anatomy. Despite all these challenges, blue whales breathe with an efficiency that borders on the extraordinary. Their respiratory system is tuned to extract maximum value from each breath. But efficiency does not eliminate limits, it only pushes them farther back. The edge of the possible is not crossed by ignoring constraints, but by aligning behaviour with them. Blue whales do not fight their respiratory limits. They live within them. Their slow movements, long dives, and surface intervals are all expressions of a body that knows exactly how much it can afford. This delicate balance becomes even more apparent when conditions change. Increased water temperature, altered prey distribution, or disturbances that force more frequent surfacing can disrupt the rhythm. What seems like a minor inconvenience can become a significant physiological stress. Breathing at this scale is not just a background process, it is a governing factor. It dictates pace, it shapes strategy, it defines what is possible and what is not. And even when oxygen can be gathered, stored and delivered effectively, another problem remains. A body this large does not just need to stay alive. It needs to generate enough energy to sustain itself. That energy must come from food, and feeding at this scale introduces challenges that are just as severe as any imposed by gravity or respiration. Because breathing may keep the body running, but feeding is what keeps it running long term, and for the blue whale, feeding is where the margin between survival and impossibility becomes especially thin. The heart is often described as a pump, and in simple terms that description works. It contracts, it moves blood, it keeps oxygen and nutrients circulating. But at the scale of a blue whale, the word pump begins to feel inadequate. The blue whale's heart is not just large. It is operating at the edge of what a biological pump can plausibly do without tearing itself apart or exhausting the tissues it serves. A blue whale's heart can weigh around 180 kilograms, sometimes more. That places it in the same mass range as a small car engine. But unlike an engine, it cannot be turned off for maintenance. It cannot pause to cool down. It cannot be overbuilt with thick metal walls and redundancy. It is made of living muscle that must contract rhythmically for decades without failing. The sheer size of the heart introduces immediate complications. Muscle fibers can only contract and relax at certain speeds. Electrical signals that coordinate contraction travel at finite rates. In a very large heart, those signals must travel longer distances, which limits how fast the heart can beat while still remaining synchronized. If different regions contract out of sequence, efficiency drops and damage can occur. This is one reason blue whale hearts beat slowly. At rest, the heart rate may fall to just a few beats per minute. During dives, it can slow even further. Each beat, however, moves an enormous volume of blood. The heart does not rely on speed, it relies on scale. This strategy reduces wear on the heart muscle and conserves energy, but it also introduces rigidity. A slow-beating heart cannot rapidly increase output in response to sudden demands. There is no quick acceleration. The system is built for steady-state operation, not bursts. The structure of the heart reflects this. The walls are thick enough to generate pressure, but not excessively so. Over-thickening would increase stiffness and reduce filling efficiency. The chambers are large, allowing significant blood volume to be moved with each contraction. Valves are reinforced to handle pressure without leaking, yet flexible enough to open and close reliably over millions of cycles. Blood itself becomes part of the engineering problem. A blue whale has thousands of litres of blood circulating through its body. This blood must be kept moving continuously. Stagnation leads to clotting. Excessive pressure leads to vessel damage. The viscosity of blood places limits on how fast it can be moved without excessive resistance. To manage this, blue whales rely on elastic arteries that stretch during each heartbeat and recoil between beats. This smooths blood flow and reduces peak pressure. It also allows the heart to work against a more consistent load rather than sharp pressure spikes. This elasticity is crucial at large scales, where rigid vessels would fail quickly. Distance remains a persistent issue. Blood leaving the heart must travel meters to reach distant tissues. Pressure drops occur along the way. To compensate, the initial pressure must be sufficient, but not so high that it damages vessels closer to the heart. This creates a narrow operating window. The vertical orientation of the body adds complexity. When a whale is oriented vertically in the water, blood must be pumped upward against gravity to reach the brain and upper tissues. Pressure differences develop between the upper and lower body. Specialized valves and vessel structures help manage these gradients, preventing pooling or insufficient flow. During dives, the circulatory system undergoes further adjustments. Blood flow is redistributed away from less critical tissues toward the brain and heart. Peripheral vessels constrict, reducing oxygen consumption where it is least needed. This prioritization extends dive time but places additional strain on central circulation. The heart must remain stable under these changing conditions. It must function during periods of low oxygen availability, altered blood chemistry, and shifting pressures. Unlike mechanical systems, it cannot isolate itself from these changes. It must respond smoothly. without hesitation. One of the most remarkable aspects of the blue whale's heart is not its size, but its restraint. It does not operate near its maximum capacity most of the time. It runs conservatively, preserving margins. This is essential for longevity. Constant high output would accelerate wear and increase the risk of failure. Even with this conservative approach, the heart remains a point of vulnerability. Disruptions to rhythm, changes in blood composition, or damage to vessels can have cascading effects. At this scale, there is little redundancy. A significant cardiac event is unlikely to be survivable. The heart's integration with breathing is also critical. Oxygen uptake at the lungs must align with circulation rates. If blood flows too quickly through the lungs, oxygen exchange becomes inefficient. If it flows too slowly, tissues are starved. Synchronizing these processes across such a large body is non-trivial. During surfacing, when the whale takes rapid breaths, circulation must adjust to absorb oxygen efficiently. During dives, circulation must slow and redistribute. The heart sits at the center of this coordination, responding to signals from the nervous system and chemical cues in the blood. Temperature affects the heart as well. Cold water helps dissipate heat, but excessive cooling can reduce muscle performance. Blood flow helps regulate temperature, carrying warmth from the core to the periphery and back. This adds another layer of demand to the circulatory system. The evolutionary path to this heart was not direct. Early whales were much smaller, with hearts that operated within more familiar ranges. As body size increased over millions of years, the heart had to adapt incrementally. Each increase in size required adjustments in chamber volume, wall thickness, valve strength, and electrical conduction pathways. There were likely limits encountered along the way. Sizes that proved unsustainable would have been selected against. Only configurations that maintained reliable circulation survived. The result is not an optimized machine in the engineering sense, but a workable compromise shaped by constraints. This helps explain why the blue whale heart cannot simply scale further. Making it larger would not solve the problem. Signal delays would increase, structural stresses would rise, efficiency would drop. There is a point beyond which biological pumping becomes impractical. The heart also ties into behaviour. Because circulation cannot ramp up instantly, blue whales avoid sudden exertion. Their feeding strategy minimises the need for prolonged high-output activity. Their migration patterns favour steady movement rather than sprinting. Everything aligns with the heart's capabilities. When people imagine the largest animal that ever lived, they often picture strength and power. But the heart tells a subtler story. It speaks of restraint, balance, and narrow margins. It is not overpowering the system, it is barely holding it together. This perspective shifts how the blue whale is understood. Its size is not a triumph of excess. It is a carefully maintained state that depends on every component working within tight tolerances. The heart is a central example of this. Large enough to move blood across a massive body, but slow and measured enough to avoid self-destruction. And even with a heart capable of this extraordinary feat, the body still faces another challenge that cannot be solved internally. Circulation can deliver oxygen and nutrients, but it cannot create them. Energy must be acquired from the environment, and at this scale the demands are immense. The heart may keep the system running moment to moment, but feeding is what keeps it running across seasons and years. Without a way to efficiently gather enough energy, even the most impressive circulatory system would be irrelevant. Feeding is where the question of size becomes unavoidable. Bones can be reinforced, muscles can be reorganized, blood can be moved more efficiently, but none of that matters if the body cannot bring in enough energy to pay for its own upkeep. At extreme scale, feeding is not just a daily activity. It is the central problem around which everything else must be arranged. A blue whale is not merely large, it is metabolically expensive. Even with a relatively slow metabolism for its size, maintaining body temperature, circulating blood, repairing tissues, and moving through the ocean requires enormous amounts of energy. That energy has to come from somewhere, and it has to arrive reliably. At first glance, this seems like an obvious point of failure. Large predators usually rely on large prey. Lions hunt large herbivores. Orcas hunt seals and whales. The logic feels straightforward. Bigger bodies require bigger meals. But blue whales break this pattern completely. They feed almost exclusively on some of the smallest animals in the ocean. Krill are tiny crustaceans, usually only a few centimeters long. Individually, they are nutritionally insignificant. A single krill contains a negligible amount of energy. By any normal standard, they are not the kind of food you would expect to sustain the largest animal that has ever lived. This mismatches the puzzle. How does an animal weighing more than 100 tons survive on prey so small that thousands of them could fit inside your hands? The answer is not found in the krill themselves, but in how they are distributed and how the whale interacts with them. Krill do not exist evenly throughout the ocean. They form dense swarms, sometimes stretching for kilometers, containing millions or even billions of individuals packed closely together. These swarms are not random. They form in regions where ocean currents, nutrient availability, and primary productivity align. In these places, microscopic phytoplankton flourish, and krill follow. For most predators, such dense prey patches are a bonus. For blue whales, they are a requirement. Feeding only works if the prey density is high enough to make each feeding attempt energetically profitable. Chasing scattered prey would cost more energy than it provides. This is where the blue whale's feeding strategy becomes crucial. Instead of picking off individual prey, blue whales feed by engulfment. They accelerate toward a dense swarm of krill, open their mouths, and take in an enormous volume of water along with everything suspended in it. Their throat pleats expand dramatically, allowing the mouth and throat to balloon outward. In a single lunge, a blue whale can take in a volume of water equal to or greater than its own body volume. Once the mouth closes, the whale pushes the water out through baleen plates, comb-like structures made of keratin that hang from the upper jaw. The water escapes, but the krill are trapped. The whale then swallows the concentrated mass of prey. This method allows the whale to harvest thousands of calories in a single action, but it comes at a cost. Accelerating such a large body requires energy. Expanding the throat pleats requires energy. Pushing water back out requires energy. If the prey density is not high enough, the energy gained from the krill would not offset the energy spent during the lunge. This means feeding opportunities are not flexible. Blue whales cannot simply graze continuously or forage casually. They must locate dense krill patches and exploit them efficiently. When conditions are right, this works extraordinarily well. When conditions are poor, feeding becomes impossible. This dependence on prey density is one of the most important constraints on blue whale size. Larger bodies require more energy, which requires denser prey patches, which are not infinitely available. The ocean can only concentrate biomass so much. Past a certain point, there is no way to gather enough energy quickly enough, no matter how efficient the feeding mechanism. This helps explain why blue whales reached their size only relatively recently in evolutionary terms. Fossil evidence suggests that the largest whales appeared after major changes in ocean ecosystems. Cooling climates, shifting currents, and increased nutrient upwelling led to higher primary productivity in certain regions. This created larger and more reliable krill swarms. In other words, the ocean became rich enough, in very specific places, to support animals of extreme size. Before that, the energy simply was not there in the right form. Even now, blue whales do not feed constantly. They follow seasonal cycles. During feeding seasons, often in colder, nutrient-rich waters, they eat enormous quantities of krill, sometimes consuming several tons per day. During other times, such as migration and breeding periods, they may eat very little, relying on stored energy in the form of blubber. This feast and famine strategy reduces the need for constant feeding, but increases dependence on successful feeding seasons. If those seasons are disrupted, the consequences can be severe. a missed feeding opportunity is not easily recovered. The mechanics of feeding also impose limits on behaviour. Lunge feeding is energetically expensive and physically demanding. It places stress on muscles, joints, and connective tissues. The throat, pleats, and jaw structures must withstand repeated extreme expansion and contraction without damage. Overuse or poor conditions could lead to injury. This is another reason why blue whales feed selectively. They do not lunge indiscriminately. They assess prey density, often using sensory cues, and only commit to a feeding maneuver when the payoff is likely to be high. There is also the issue of time. Each lunge takes time to execute and recover from. The whale must accelerate, engulf, filter, swallow, and then reposition. During this time, it is not actively feeding. The efficiency of feeding depends not just on how much prey is captured, but on how quickly the cycle can be repeated without exhausting oxygen stores. Feeding is therefore tightly linked to breathing and circulation. Lunges must be timed within dive limits. Recovery must allow oxygen levels to stabilize. The heart must support repeated exertion without overloading. All of these systems converge during feeding. This convergence creates a narrow window where feeding is possible and profitable. Outside of that window, the strategy fails. This is why blue whales are often found in specific regions at specific times. Their movements track the availability of dense prey, not convenience or preference. The puzzle deepens when you consider why no other animal has taken this strategy further. If feeding on tiny prey through engulfment works so well, why not become even larger? Why stop where blue whales stopped? The answer lies in diminishing returns. As body size increases, the volume of water that must be moved increases faster than the volume of prey captured, unless prey density increases accordingly. At some point, the energy cost of each lunge would exceed the energy gained, even in the densest swarms. The ocean simply cannot pack enough food into a small enough space to support an even larger body. There are also mechanical limits. The jaw, throat pleats, and baleen structures can only expand so much before structural integrity is compromised. Scaling these structures further would require changes that may not be biomechanically feasible. In this sense, feeding sets one of the hardest ceilings on size. It is not a gradual pressure, it is a hard constraint. Either the environment provides enough concentrated energy, or it does not. The blue whale exists because for now, the ocean still produces krill swarms dense enough to make its feeding strategy viable. But this balance is delicate. Changes in ocean temperature, acidity, and circulation patterns can affect krill populations. Small shifts at the base of the food web can ripple upward, affecting the largest consumer. This vulnerability underscores how close to the edge blue whales live. Their size is not supported by abundance everywhere. It is supported by abundance in just the right places, at just the right times. Feeding something so vast is not a simple matter of eating more. It is a complex alignment of anatomy, behavior, and ecology. It requires the environment to cooperate in very specific ways. When it does, the impossible becomes possible. When it does not, even the largest animal that ever lived must wait, conserve, and hope the next opportunity arrives. And even when food is available and feeding works as intended, another question remains. Why does the ocean, of all places, allow this strategy to succeed? What is it about water itself that changes the rules enough to make extreme size workable? Because feeding is not just about prey, it is about the medium in which feeding happens. And that medium plays a role far larger than it first appears. The ocean does not simply host large animals, it reshapes what large even means. On land, size is negotiated almost entirely within the constraints of gravity, friction, and limited energy availability. In water, those same forces behave differently. They do not disappear, but they are redistributed in ways that open doors that would otherwise remain closed. The most obvious difference is buoyancy. Water supports weight. An object submerged in water experiences an upward force equal to the weight of the water it displaces. For small animals, this is a mild convenience. For very large ones, it is transformative. It means that mass does not translate directly into stress on bones and joints. It means bodies can grow heavier without collapsing under their own weight. This does not mean gravity stops acting. The whale is still massive, its tissues still have weight. But the ocean absorbs a large fraction of that weight continuously, passively, without requiring muscular effort. This fundamentally alters the economics of size. Instead of constantly paying the cost of support, the animal receives support for free from its environment. This single shift cascades into many others. Because bones no longer need to bear full body weight, they do not need to be proportionally as thick or dense as those of land animals of similar mass. This reduces skeletal mass, which reduces overall weight, which further reduces stress. A feedback loop appears, but this time it works in favour of size rather than against it. Movement changes as well. On land, moving a large body requires lifting and placing weight with each step. This involves repeated acceleration and deceleration against gravity. In water, movement is primarily about pushing against a fluid. The body is already supported. Muscles generate thrust rather than lift. Energy goes into overcoming drag rather than fighting gravity. Drag does increase with size, but not in the same punishing way that gravity does on land. Drag scales with surface area and speed. It can be managed through shape and behaviour. Long, streamlined bodies reduce turbulence. Slow, steady movement minimises resistance. The ocean rewards smoothness rather than strength. This is why the largest animals are not bulky or angular. They're elongated, tapered and fluid in form. The blue whale's shape is not an aesthetic choice. It is a response to the physics of moving through water efficiently at large scale. Any deviation would increase drag and energy cost. Water also changes how heat is managed. It conducts heat far more effectively than air. For small animals, this is a disadvantage. Heat is lost quickly, increasing metabolic demands. For large animals, this becomes an asset. Excess heat generated by muscle activity and metabolism can be shed more easily. The ocean acts as a thermal buffer, smoothing temperature extremes. This thermal stability allows large bodies to maintain consistent internal conditions without overheating. It also allows for thick layers of insulating blubber without trapping dangerous amounts of heat. The same blubber that stores energy and aids buoyancy also interacts with water to regulate temperature more effectively than it would in air. Sound behaves differently in water as well. It travels faster and farther. This matters because large animals benefit from long-range communication. Blue whales use low-frequency sounds that can travel hundreds of kilometres. This allows individuals to locate each other across vast distances without expending energy on constant movement. While sound is not directly tied to size, it supports the social and reproductive behaviours that make large body plans viable. Finding mates, coordinating movement, and maintaining spacing all become easier when communication is efficient over long distances. The ocean also reshapes food distribution. On land, energy is spread across plants rooted in place. Herbivores must move to find food. Predators must chase prey that can flee in multiple directions. In the ocean, microscopic organisms form the base of the food web, drifting with currents. Energy can be concentrated vertically and horizontally through physical processes like upwelling and mixing. These processes create dense, predictable prey aggregations that can be exploited by large filter feeders. The ocean, in effect, does part of the work of gathering food. It brings nutrients to the surface, it concentrates biomass, it creates feeding opportunities that would not exist on land. Time behaves differently in water as well. Large aquatic animals can move slowly without consequence. There is no need to outrun predators constantly. Buoyancy allows rest without collapse. Energy can be conserved through extended gliding and minimal movement. This favours endurance over speed. All of this lowers the baseline cost of being large. It does not remove limits, but it shifts where those limits lie. On land, the ceiling arrives early and abruptly. In water, it arrives later and more gradually, allowing evolution to explore larger sizes before encountering hard constraints. But the ocean is not infinitely forgiving. Its support depends on being immersed. Remove that immersion, and the advantages vanish instantly. This is why aquatic giants are so specialized. Their bodies are tuned for a medium that must always be present. The ocean also imposes its own rules. Visibility is limited, pressure increases with depth, salinity affects buoyancy, currents impose forces that must be navigated. Large bodies must be strong enough to handle these conditions without being rigid. Pressure in particular increases rapidly with depth. While blue whales do not dive as deep as some smaller whales, they still experience significant pressure changes. Their tissues must compress and re-expand without damage. Air spaces must collapse safely. Blood vessels must tolerate changing external pressure. Water density also varies with temperature and salinity. Buoyancy is not constant. The whale's body must adapt to these variations subtly, adjusting posture and movement to maintain stability. This requires fine control over body orientation and muscle tension. Another quiet but important difference is how injuries behave in water. On land, wounds are exposed to air, pathogens, and debris. Movement can reopen injuries. In water, healing conditions differ. This does not make injury trivial, but it alters recovery dynamics in ways that can benefit large, slow-moving animals. The ocean also reduces the effectiveness of many predators. Large size combined with water's resistance makes rapid attacks difficult. Even predators that could theoretically harm a blue whale face significant energetic costs and coordination challenges. This reduces predation pressure on adults, allowing size to function as a long-term survival strategy. Importantly, the ocean allows size without requiring dominance. Blue whales are not aggressive. They do not fight for territory. They do not rely on strength to control others. Their size exists alongside a relatively gentle behavioral profile. This is possible because the environment reduces competition and direct conflict. On land, large size often leads to conflict over space and resources. In the open ocean, space is vast. Resources are patchy but shared. Size does not provoke the same competitive dynamics. All of these factors combine to change the rules under which size evolves. The ocean does not encourage bigness by default. It tolerates it under specific conditions. When those conditions align, size becomes viable. When they do not, even water cannot save it. This helps explain why extreme size has appeared so rarely, even in the ocean. Many marine animals are large, but only one lineage reached this scale. The rules may be different, but they are still strict. The blue whale exists because it operates within a narrow corridor of possibility created by the ocean's physical properties. Buoyancy reduces weight. Drag can be managed through shape. Heat can be shed. Food can be concentrated. Communication can span great distances. Movement can be slow and economical. Remove any one of these supports, and the corridor narrows sharply. Remove several, and it closes entirely. Understanding why the ocean changes the rules makes it clear that the blue whale is not simply the result of biological ambition. It is the result of environmental permission. The medium allows what land forbids. And yet, even with these advantages, the whale's existence remains conditional. The ocean must continue to behave in certain ways. Currents must bring nutrients. Temperatures must remain within bounds. Ecosystems must remain intact. This fragility is easy to overlook when confronted with sheer size. But size, in this case, is not armor. It is a dependence. The whale's body is shaped by water so completely that it cannot exist without it. As we move further, it becomes important to look at this relationship more closely. Not just how water supports mass, but how it actively participates in the whale's survival. Because the ocean is not just a setting, it is part of the whale's anatomy in everything but name. And that relationship between body and medium reveals why this particular form of life could only have emerged where it did. and why it remains such a rare and delicate outcome. Water does more than surround the blue whale. It carries it, shapes it, and quietly absorbs demands that the whale's body could never meet on its own. This support is so constant and so complete that it becomes easy to overlook, but without it, the entire system collapses almost instantly. Water is not just an environment here, it is an external structure, an invisible framework that completes the animal. The most obvious way water provides support is through buoyancy, but buoyancy is often misunderstood as a simple lifting force. In reality, it is a continuous redistribution of load. Every cubic metre of water displaced by the whale pushes upward with a force equal to its weight. That force acts across the entire body, not at a single point. This means the whale's mass is not concentrated onto bones and joints in the way it would be on land. It is spread out, diffused, shared with the surrounding medium. This distribution matters enormously. On land, weight funnels through specific pathways: feet to legs, legs to hips, hips to spine, spine to ground. Each link in that chain experiences enormous compressive forces. In water, there is no equivalent chain. Support comes from all directions at once. The body floats within a pressure field that adjusts automatically as the whale moves. Because of this, the whale does not need rigid internal bracing. It does not need column-like limbs or reinforced joints designed to lock under load. Its skeleton can remain relatively flexible. Its spine can undulate. Its ribs can move. This flexibility is not a luxury. It is essential for efficient swimming and for tolerating the constant motion of the ocean. Water also supports the whale dynamically, not just statically. When the whale moves, water flows around it, generating lift forces similar to those experienced by aircraft wings. The shape of the body, the angle of the flukes, and the curvature of the torso all interact with moving water to generate subtle upward and stabilizing forces. These forces reduce the effective weight even further during motion. This dynamic support allows the whale to glide. After a powerful tail stroke, it can coast forward, supported by momentum and hydrodynamic lift, without continuous muscular effort. This conserves energy and reduces strain on tissues. Over long distances, these small savings accumulate into something substantial. Pressure plays a role as well. As depth increases, water pressure rises uniformly across the body. This external pressure counteracts internal pressures, stabilizing tissues and reducing the tendency for structures to deform unevenly. Air-filled spaces collapse safely, while fluid-filled tissues compress slightly but evenly. This uniform compression helps prevent localized stress points. The whale's blubber interacts with water in ways that go beyond insulation. Blubber is less dense than muscle and bone. It contributes to buoyancy, helping the whale maintain neutral buoyancy at certain depths. This means the whale does not have to actively swim to avoid sinking or floating uncontrollably. It can hover with minimal effort. Neutral buoyancy is a powerful advantage. It allows rest without collapse. It allows slow movement without constant correction. It allows energy conservation in a body where energy is always at a premium. Achieving this balance requires careful tuning of body composition, and water is the medium that makes it possible. Water also dampens movement. On land, sudden shifts in posture or balance can produce sharp forces that propagate through the skeleton. In water, movement is resisted smoothly. Acceleration and deceleration are gradual. This reduces peak stresses on bones, muscles, and connective tissues. The whale's body is spared the jolts that would be unavoidable on land. This damping effect extends to collisions and impacts. While collisions at sea can still be dangerous, water reduces impact forces by spreading them out over time and space. For a large animal, this can mean the difference between tolerable strain and catastrophic injury. Again, the medium absorbs part of the cost. Even posture is supported by water. The whale does not need to actively hold itself upright. orientation can be adjusted with small movements of fins and tail. Muscles that would otherwise be dedicated to posture on land are free to focus on propulsion and steering. This reduces baseline muscular activity and energy expenditure. Water also supports internal processes. Blood circulation benefits from reduced gravitational gradients. While gravity still affects blood distribution, the effect is muted compared to land. The heart does not have to fight as hard to move blood vertically. Pressure differences across the body are smaller. This reduces stress on vessels and valves. Digestive organs benefit as well. A massive stomach full of water and krill is heavy. On land, that weight would strain connective tissues and compress organs. In water, much of that weight is offset. Organs float within the body cavity, supported by surrounding tissues and fluid pressure. This allows feeding strategies that would be untenable on land. Reproduction too is influenced by this support. Carrying a developing fetus at this scale is energetically and structurally demanding. Water helps offset the added mass. It reduces strain on the spine and internal supports. Without this assistance, gestation at such size would be far more risky. What makes this support system remarkable is that it requires no active participation from the whale. There are no muscles dedicated to buoyancy, no organs tasked with generating lift. The support is automatic. It is always present, always adjusted, always proportional to the body's needs. This creates a dependency that is absolute. The whale's body is designed with the assumption that water will always be there. Remove it, and systems fail immediately. This is why even brief stranding events are often fatal. The invisible support disappears, and the body must suddenly carry loads it was never meant to bear. The reliance on water also shapes evolutionary possibilities. Traits that would be maladaptive on land can persist and even be advantageous in water. Flexible skeletons, reduced bone density, enormous mass with limited structural reinforcement. These are not weaknesses in this context. They are adaptations to a supportive medium. At the same time, this dependency narrows options. The whale cannot exploit environments where water is shallow or absent. It cannot tolerate prolonged exposure to conditions where buoyancy is reduced or uneven. Its range is constrained by the need for continuous immersion. Water also shapes how the whale interacts with threats. Size combined with buoyancy makes rapid attack difficult. Predators must overcome not just the whale's mass, but the resistance of water itself. This reduces the frequency and intensity of predation pressure on adults, allowing size to function as a long-term strategy rather than a liability. However, this same resistance affects the whale. It limits speed and agility. It prevents rapid, evasive maneuvers. The whale accepts these trade-offs because its size and the ocean's vastness reduce the need for agility. Avoidance replaces confrontation. The invisible support system of water also extends to time. Movements are slower, processes are stretched out. Life proceeds at a measured pace. This favours long lifespans and slow reproductive cycles. It discourages rapid turnover and explosive growth. All of this contributes to a picture where the whale is not an independent structure, but part of a coupled system. Body and medium form a single functional unit. The whale's anatomy only makes sense when paired with the ocean's properties. This pairing explains why attempts to imagine even larger animals often fail. Increasing size would increase displacement, which would increase buoyancy, but it would also increase drag, feeding demands and structural complexity. The support system scales, but not without limits. At some point, the costs outpace the benefits. Water allows the blue whale to exist, but it does not encourage unlimited growth. It offers a narrow corridor of possibility, not an open invitation. The whale occupies that corridor precisely. It fills it without spilling over. Understanding water as an invisible support system reframes the question of size. The blue whale is not just a biological achievement, it is a physical partnership, a body tuned to a medium, and a medium that happens to allow such a body to persist. As we move onward, This partnership becomes even more important, because water alone does not explain how such a form came to be. It explains how it can function, but not how it emerged. For that, we have to look backward, across deep time, to the slow accumulation of changes that led from small, land-dwelling ancestors to something so vast that it redefines what life can do. The blue whale did not appear suddenly, fully formed, as if nature woke up one day and decided to test the absolute limits of size. What we see today is the outcome of an experiment that unfolded over tens of millions of years, guided not by intention or foresight, but by a sequence of small adjustments that happen to line up in a very particular way. Evolution does not plan, it tinkers, and sometimes, given enough time and the right conditions, tinkering produces something extraordinary. To understand how this experiment unfolded, it helps to begin with a reminder that whales were not always ocean giants. Their ancestors were small, land-dwelling mammals that lived near water, animals that looked more like wolves or deer than anything we would recognize as a whale. They walked on 4 legs, breathed air, and hunted or scavenged along shorelines and riverbanks. Their bodies were shaped by gravity, by the need to support weight on land, and by the demands of terrestrial life. The move into water was not driven by a desire to become large, it was driven by opportunity. Coastal and aquatic environments offered food sources that were abundant and underexploited. Over time, some of these early mammals spent more time in water, swimming, wading, and hunting aquatic prey. Natural selection favoured traits that made this easier. Stronger tails, more flexible spines, limbs that worked better as paddles, bodies that experienced less drag. At this stage, size was still modest. These early whales were not giants. They were experimenting with a new way of living, not a new scale of existence. But even then, the ocean was already changing the rules. Buoyancy reduced the penalty of added mass. Swimming rewarded streamlined shapes. Heat loss became a concern, encouraging the development of insulating tissues. As these early whales became more fully aquatic, they began to lose features that were no longer useful. Hind limbs shrank and eventually disappeared. Nostrils migrated upward, becoming blowholes. The spine became more flexible. Each change solved a local problem, but also opened new possibilities. One of those possibilities was size. In water, being slightly larger brought advantages. Larger bodies conserved heat more effectively. They could travel farther on the same amount of energy. They were less vulnerable to predators. None of this required extreme growth. It only required incremental increases that paid for themselves. Importantly, there was no single path toward becoming large. Different whale lineages explored different strategies. Some became fast predators, others specialized in suction feeding. Some remained relatively small. Evolution does not push all lineages in the same direction. It explores whatever options are locally available. The lineage that would eventually produce blue whales took a particular turn when it abandoned active predation in favor of filter feeding. This shift was not about size at first. It was about efficiency. Feeding on small prey, when those prey are abundant and densely packed, can be extremely profitable. It allows an animal to harvest energy without chasing individual targets. Filter feeding favoured changes in skull shape, jaw structure and feeding mechanics. Baleen replaced teeth, mouths grew wider, throats became expandable. These changes were advantageous even at moderate sizes. They allowed whales to exploit prey resources that other predators could not use efficiently. Once filter feeding was established, size began to matter in a new way. Larger mouths could engulf more water, larger throats could hold more prey, larger bodies could store more energy. Each increase in size made filter feeding more efficient, as long as prey density was sufficient. This created a feedback loop. As whales grew larger, they became better at exploiting dense prey patches. As they became better at feeding, they could support larger bodies. This did not happen everywhere. It only worked in environments where the ocean produced large, reliable concentrations of plankton and krill. These conditions were not always present. Changes in climate and ocean circulation played a critical role. As Earth cooled over millions of years, polar ice expanded, winds shifted, and nutrient-rich waters were brought to the surface more frequently in certain regions. This increased primary productivity, which increased krill populations. The timing matters. The largest whales appear in the fossil record relatively recently after these changes took hold. Before that, the ocean simply could not support animals of such extreme size. The experiment could not proceed until the environment cooperated. Even then, growth was gradual. Each generation inherited a body plan that was only slightly larger than before. Any increase that pushed the system beyond its limits would have been selected against. Only those configurations that maintained functional balance survived. This slow pace is important. It allowed supporting systems to adapt alongside size. Circulatory systems adjusted, skeletal structures reorganized, feeding mechanics scaled up. There was no single leap, just countless small steps, each one viable on its own. It is tempting to imagine that evolution was aiming for a maximum, that it was building toward the largest possible animal. But this is a misunderstanding. Evolution does not aim, it responds. Size increased because it worked, not because it was impressive, and it worked only under specific circumstances. Filter feeding on dense prey, living in buoyant water, migrating between feeding and breeding grounds, operating at a slow, efficient pace. Remove any of these elements and the experiment would have stalled. There were also trade-offs that came with increasing size. Larger bodies meant slower reproduction, longer development times, greater vulnerability to environmental change. These costs were acceptable only because adult survival rates were high and food was abundant. This balance could easily have tipped the other way. A prolonged decline in prey density, a shift in ocean circulation, increased predation pressure. Any of these could have made large size disadvantageous. In that case, evolution would not have continued along this path. The fact that it did continue tells us something important. The conditions that supported large whales were stable enough for long enough to allow size to increase without catastrophic consequences. This stability is rare on geological timescales. It also tells us that blue whales are not inevitable, they are contingent. They exist because a long chain of events happen to align. If history had unfolded slightly differently, the largest animals on Earth today might be much smaller. This long experiment also explains why blue whales are so specialized. They are not generalists. Their bodies are tuned to a particular way of living. They cannot easily adapt to different prey, different environments, or different behaviors. The experiment produced a narrow solution, not a flexible one. Evolution often favors flexibility, but in this case, efficiency won out. The environment rewarded a specific strategy so strongly that specialization became viable. The result is an animal that operates near the edge of what is possible but does so with remarkable consistency. It is worth noting that this experiment has no guarantee of continuation. Evolution does not protect its successes. It does not preserve what is impressive. If conditions change enough, even the largest animal that ever lived could become untenable. In that sense, the blue whale is not the endpoint of an upward trajectory. It is a snapshot, a moment when the experiment has reached its furthest extent, at least for now. Understanding evolution's role reframes the question of size. The blue whale is not a triumph over limits. It is temporary alignment with them, a configuration that works under current conditions, but only just. As we look deeper into this history, another factor becomes increasingly important. Size alone did not drive success. Timing mattered. The ancient oceans themselves had to change in ways that made extreme size energetically worthwhile. Because evolution can only work with what the environment provides. And in this case, the environment provided something new, something abundant, and something that made the impossible briefly practical. For most of Earth's history, the oceans were not the kind of place that could support something like a blue whale. They were vast, yes, but vastness alone is not enough. What matters is not how much water there is, but how energy moves through it. For an animal of extreme size to exist, the ocean has to do more than contain it. It has to feed it, predictably and in enormous quantities, over and over again, for decades at a time. If you could travel back through deep time and look at the ancient oceans, you would notice something immediately. They were often quieter in a biological sense. Life was present, sometimes abundant, but the structure of marine ecosystems was different. Energy flowed, but not always in ways that allowed it to concentrate at the scales required to sustain colossal bodies. The base of the marine food web has always been microscopic. Phytoplankton, tiny photosynthetic organisms, convert sunlight and nutrients into biomass. Everything else depends on them, either directly or indirectly. But for much of the past, this process was limited by the availability of nutrients near the surface. Large areas of the ocean were effectively biological deserts, clear and blue but low in productivity. Nutrients tend to sink. Dead organisms, waste products and organic debris fall toward the deep ocean, taking nitrogen, phosphorus and iron with them. Without a mechanism to bring those nutrients back to the surface, primary productivity stalls. Phytoplankton growth slows. Everything above them shrinks accordingly. For millions of years, this created a ceiling. Marine ecosystems could support fish, reptiles, and early whales, but not at the densities required for extreme size. Large predators existed, but they were constrained by the need to hunt sizable prey individually. Filter feeding at massive scale simply would not have paid off. What changed was not a single event, but a series of shifts that altered how the ocean circulated and how nutrients were redistributed. As Earth's climate cooled over long timescales, temperature differences between the equator and the poles increased. These differences strengthened winds and intensified ocean currents. Cold, nutrient-rich waters from the deep were brought to the surface more frequently, especially in high-latitude regions and along continental margins. This process, known as upwelling, transformed parts of the ocean. Areas that had once been relatively unproductive became hotspots of life. Phytoplankton blooms intensified. Zooplankton populations followed. Krill, which feed on phytoplankton, began to form larger and more consistent swarms. These swarms were not just larger than before, they were denser. That density is crucial. It is the difference between a feeding strategy that barely breaks even and one that produces a surplus large enough to support extreme growth. At the same time, changes in ocean chemistry played a role. Increased availability of certain nutrients allowed phytoplankton communities to shift towards species that were particularly good at supporting higher trophic levels. The efficiency of energy transfer through the food web improved, meaning more of the energy captured at the surface made its way into animal biomass rather than being lost along the way. The physical structure of the ocean also mattered. Expanding polar ice influenced circulation patterns, creating predictable seasonal cycles. During certain times of year, productivity would spike dramatically. These seasonal pulses created windows of abundance that large animals could exploit by feeding intensively and storing energy for leaner periods. This is where the idea of colossal opportunity comes into focus. The ocean did not become uniformly rich. It became patchy in a very specific way. Enormous amounts of food were available, but only in certain places at certain times. This rewarded animals that could travel long distances, arrive at the right moment, and feed efficiently on dense prey. Large size suddenly became an asset rather than a burden. Bigger bodies could migrate farther without stopping. They could store more energy as blubber. They could endure long fasting periods. They could afford to specialize in feeding strategies that depended on rare but massive payoffs. This shift did not favor all marine animals equally. It favored those already inclined toward filter feeding and long-distance travel. Baleen whales were uniquely positioned to take advantage of these changes. They already had the basic tools. the ancient oceans simply amplified the payoff. As productivity increased, so did the potential benefits of increasing size. Larger mouths meant more water engulfed per feeding event. Larger bodies meant greater storage capacity. Larger animals could dominate feeding opportunities simply by being able to exploit them more efficiently than smaller competitors. But this opportunity was tightly bounded. It existed because the ocean had reached a particular state, one that balanced nutrient supply, circulation and climate. Too little productivity and large size would not pay. Too much instability and the system would collapse before large animals could benefit. The fossil record reflects this balance. The appearance of truly gigantic whales coincides with periods of high sustained ocean productivity. Before that, whales were diverse, but smaller. After that, the lineage producing the largest forms flourished, while others remained moderate in size or disappeared. This tells us that size was not just a biological innovation, it was an ecological response. The environment offered a new set of rewards, and evolution responded by exploring them as far as it could. It also explains why this exploration did not continue indefinitely. Even in the most productive oceans, there are limits to how much energy can be concentrated in one place. Krill swarms can only become so dense. Feeding events can only become so efficient. At some point, further increases in size would not yield additional returns. Ancient oceans provided a corridor of possibility, not an open plain. Whales grew into that corridor and filled it. They did not outgrow it. Another important factor is time. These changes unfolded slowly. Ocean circulation patterns evolved over millions of years. Ecosystems adjusted gradually. This slow pace allowed evolutionary responses to keep up. Whales did not need to leap across gaps. They could follow the shifting landscape step by step. This gradualism is essential. Sudden changes tend to favour flexibility and small size. Large, specialised organisms struggle to adapt quickly. The ancient oceans changed slowly enough to allow specialisation to deepen, without immediate penalty. There is also a geographical dimension to this story. The most productive regions of the ocean are not evenly distributed. They cluster along certain coastlines and polar regions. Blue whales and their relatives evolved behaviours that allowed them to track these regions across vast distances. Migration became part of the solution. By moving between feeding and breeding grounds, whales could exploit seasonal abundance without remaining in harsh environments year-round. This reduced risks associated with cold, storms and ice, while preserving access to dense prey. These migrations would have been impossible for smaller animals relying on scattered food sources. Size enabled endurance, endurance enabled migration, migration enabled access to colossal opportunities. When viewed this way, the blue whale's size begins to look less like an accident and more like a measured response to a temporary alignment of conditions. The ancient oceans did not invite unlimited growth. They offered just enough support to make extreme size workable, as long as every other system cooperated. This cooperation extended beyond feeding. Stable productivity allowed long lifespans. Predictable prey allowed slow reproduction. Reduced predation pressure allowed energy to be invested in growth rather than defense. Each piece reinforced the others, but this balance remains fragile. The same factors that created opportunity can reverse. Changes in temperature can alter circulation. Acidification can affect plankton communities. Disruptions at the base of the food web can propagate upward, with disproportionate effects on the largest consumers. Understanding the role of ancient oceans helps explain why blue whales are not just large animals, but products of a specific moment in Earth's history. They exist because the ocean, for a time, became capable of supporting them. This realization shifts the narrative again. The blue whale is not simply a biological marvel, it is a geological and climatic one as well. Its body is a record of ocean conditions written in flesh and bone, and as we move forward, this connection becomes even more intimate. Because once size crossed a certain threshold, Survival depended not just on abundance, but on efficiency. Energy had to be captured, stored, and used with minimal waste. The next piece of the puzzle lies in how a body this large manages its energy budget so carefully, extracting maximum value from tiny prey and converting it into sustained existence. At extreme size, energy stops being a background consideration and becomes the governing principle. Every movement, every breath, every physiological process carries a cost that must be paid repeatedly, day after day, year after year. For a blue whale, the margin between gain and loss is narrow. Efficiency is not a preference. It is the difference between viability and impossibility. Krill sit at the centre of this equation. They are small, fragile, and individually insignificant, yet collectively they form one of the most important energy reservoirs in the ocean. Blue whales do not succeed despite eating krill. They succeed because they eat krill in a way that extracts energy with extraordinary efficiency. To understand why this works, it helps to think in terms of energy density and energy capture. Krill are rich in lipids, particularly during certain seasons. These fats are high-energy molecules, exactly the kind needed to support large bodies and long fasting periods. But the energy is dispersed across millions of tiny bodies. The challenge is not the quality of the energy, but the logistics of gathering it. Most predators solve energy capture by selecting individual prey and subduing it. This approach scales poorly. Catching and handling prey takes time and effort. As body size increases, the cost of pursuit rises, while the speed and agility needed to catch prey become harder to maintain. At some point, the math stops working. Blue whales bypass this problem entirely. They do not pursue individual prey. They pursue density. Their feeding strategy treats the ocean itself as a container, harvesting whatever energy happens to be concentrated within it at that moment. This is not hunting in the traditional sense. It is bulk energy extraction. The mechanics of lunge feeding are central here. When a blue whale lunges, it accelerates rapidly relative to its usual pace, opening its mouth wide and engulfing a massive volume of water. The throat pleats expand outward, stretching tissues that are normally folded tight. The mouth becomes a temporary storage chamber, larger than many rooms. This expansion is not passive. It requires muscular effort to control and stabilize. Water is heavy. A single engulfment can involve tens of tons of water. Managing that mass without losing control or damaging tissues is a remarkable feat of biomechanics. Once the mouth closes, the whale does something equally important. It slows down. The water captured must be expelled through the baleen, which acts as a filter. This process takes time and energy, but it allows the whale to separate prey from water with minimal loss. The key to efficiency lies in the ratio between energy gained and energy spent. If prey density is high, the energy gained from krill far exceeds the cost of the lunge. If density is low, the opposite is true. This binary outcome forces selectivity. Blue whales cannot afford mediocre feeding opportunities. They must wait for exceptional ones. This selectivity shapes behavior. Blue whales often feed in specific locations where krill reliably aggregate. They may spend long periods travelling or searching, punctuated by intense feeding bouts when conditions are right. This pattern maximizes efficiency by minimizing wasted effort. Energy efficiency also appears in how blue whales move between feeding events. They swim slowly. They glide when possible. They avoid unnecessary acceleration. Their movement patterns are tuned to minimize drag and conserve oxygen. Over long distances, these small savings accumulate. Another layer of efficiency comes from scale itself. Larger bodies lose heat more slowly. This reduces the energy needed to maintain body temperature, especially in cold waters. What might be a liability for smaller animals becomes an advantage here. Energy that would otherwise be spent on thermoregulation can be diverted to growth and maintenance. Blubber plays a crucial role in this energy economy. It is not just insulation, it is storage. During feeding seasons, blue whales convert surplus energy into thick layers of fat. This energy reserve can sustain them through migrations and breeding periods when feeding is minimal or absent. This ability to store energy efficiently reduces dependence on constant food intake. It allows blue whales to exploit seasonal abundance without being trapped in place. They can travel thousands of kilometers, relying on stored reserves, and then replenish those reserves when conditions allow. The metabolic rate of blue whales is another piece of the puzzle. While their absolute energy consumption is enormous, their mass-specific metabolic rate is relatively low. Each kilogram of whale tissue consumes less energy than a kilogram of tissue in a smaller animal. This scaling effect is critical. It means that doubling body mass does not double energy demand per unit mass. However, this advantage has limits. At some point, total energy demand becomes so high that even efficient feeding cannot keep up. This is where size meets its ceiling. Blue whales appear to be near that ceiling. Any significant increase in size would require either denser prey, more efficient feeding, or a lower metabolic cost than biology likely allows. There is also a mechanical efficiency component. The Blean filtering system is passive once water is moving through it. Unlike chewing or tearing flesh, filtering requires relatively little active effort per unit of prey captured. This allows large volumes to be processed with minimal additional cost. Contrast this with land herbivores, which must chew continuously, process fibrous material, and ferment plant matter over long periods. Their feeding is time-intensive and metabolically costly. Blue whales compress feeding into discrete high-yield events. This compression reduces exposure to risk and minimizes time spent in energetically expensive behaviors. It also allows the whale to coordinate feeding with optimal physiological states, such as high oxygen availability and favorable body orientation. Efficiency extends even to waste. Blue whales digest krill effectively, extracting a high proportion of available energy. Waste products are expelled back into the ocean, where they contribute nutrients that support plankton growth. This recycling subtly reinforces the system that feeds them. From an ecological perspective, blue whales are not just consumers, they are participants in nutrient cycling. Their feeding and excretion help redistribute nutrients vertically and horizontally, supporting the very productivity they depend on. This feedback does not create krill swarms on its own, but it enhances existing processes. This interconnectedness underscores how finely balanced the system is. Energy flows from sunlight to phytoplankton to krill to whale. At each step, losses occur. Only because those losses are minimized, and because productivity is high, does enough energy reach the top to support such a large consumer. Any disruption along this chain has amplified effects. A decline in phytoplankton reduces krill abundance. A shift in krill distribution reduces feeding efficiency. Increased energy costs from disturbance or environmental change erode margins. For an animal operating near energetic limits, small changes matter. This is why blue whales are so sensitive to changes in ocean conditions. Noise pollution that forces longer dives or disrupts feeding patterns. Climate shifts that alter krill distribution. Human activity that reduces prey availability. Each of these increases energy expenditure or reduces intake, pushing the system closer to failure. The success of blue whales is not a story of excess. It is a story of balance. They exist because their energy budget works, not because it is generous. There is no large surplus. There is careful accounting. When viewed this way, the blue whale's feeding strategy looks less like abundance and more like precision. Every aspect of its behavior, anatomy, and physiology is aligned toward making a difficult equation come out just barely positive. Energy, efficiency, and eating krill are inseparable in this story. Remove one, and the others collapse. The whale's size depends on all three functioning together consistently across a lifetime, and this brings us to an important contrast. If the ocean can support size so effectively, why did this path never succeed on land? Why did terrestrial environments, despite abundant plant life and long evolutionary history, never produce anything comparable? The answer lies in how energy is gathered, stored and spent when water is no longer there to share the load. On land, the idea of something like a blue whale stops making sense almost immediately, not because land lacks space or food or time, but because the rules that govern life on land are far less forgiving. The same forces that water softens and redistributes become direct and uncompromising. Size on land is not negotiated, it is enforced. The most obvious difference is gravity, but gravity on land is not just stronger in effect, it is more focused. Weight has to go somewhere. It travels through specific structures, down specific pathways, into specific points of contact with the ground. Feet, joints, bones, ligaments. There is no diffusion of force across a surrounding medium. Every kilogram has to be carried internally, continuously. As land animals grow larger, their skeletons must become disproportionately thicker to support the added mass. But this thickening does not scale cleanly. Bone strength increases with cross-sectional area, while body mass increases with volume. That mismatch means that every increase in size demands a greater and greater investment in structural support, until support itself becomes a major portion of the body's mass. This creates a feedback loop that quickly becomes prohibitive. Thicker bones add weight. Added weight requires thicker bones. Muscles must grow stronger to move those heavier bones. Stronger muscles add more mass. The system spirals toward inefficiency long before reaching extreme scales. Dinosaurs came closer than any other land animals to pushing this limit, but even the largest sauropods were constrained. Their bodies were supported by column-like limbs designed to minimize bending stress. Their movement was slow and deliberate. Their posture was rigid. Even then, their size was bounded. They could not afford flexibility, agility, or redundancy. Land also imposes constant mechanical shock. Every step produces impact forces that travel up the skeleton. For small animals, these forces are easily absorbed. For large ones, they accumulate. Joints wear down. Cartilage degrades. Microfractures form in bone. Repair takes time, and time is limited when damage is ongoing. Water removes most of this problem. On land, there is no equivalent buffer. The ground does not yield. It does not slow motion gently. It reflects force back into the body. Over decades, this becomes a serious liability. Heat is another critical factor. Large bodies generate large amounts of metabolic heat. On land, shedding that heat is difficult. Air is a poor conductor compared to water. Cooling relies on evaporation, convection and radiation, all of which are less efficient in still or warm conditions. This is why large land animals struggle in hot environments. They rely on behavioral adaptations like shade seeking and reduced activity during peak heat. Even then, overheating remains a constant risk. There is a limit to how much heat a large terrestrial body can safely dissipate. The blue whale's solution, using water as a thermal sink, simply does not exist on land. Thick blubber would be disastrous. Large muscles working against gravity would generate heat faster than it could be lost. Sustained activity would become dangerous. Breathing adds another layer of constraint. On land, breathing can be continuous, but oxygen delivery still faces limits imposed by circulation. Blood must be pumped vertically through the body against gravity. In very large animals, maintaining sufficient blood pressure without damaging vessels becomes increasingly difficult. The giraffe, often cited in this context, already operates near the limit of what is feasible. Its heart generates extremely high blood pressure to deliver oxygen to its brain. Its vessels are reinforced. Specialized valves prevent blood from pooling. Even so, its size remains modest compared to aquatic giants. Scaling the system up to the size of a blue whale would be untenable. The heart would need to generate pressures that living tissue could not tolerate. Vessel walls would have to be impossibly strong. The risk of failure would be constant. Feeding on land also imposes different constraints. While plant biomass is abundant, it is diffuse. Grazing animals must move continuously to gather enough food. Digesting plant material takes time and space. Fermentation chambers must be large and active. This limits how quickly energy can be extracted. Predators face even steeper challenges. Chasing large prey requires speed, agility, and endurance. At large sizes, these traits are mutually exclusive. A massive predator would be slow. A slow predator would starve. Filter feeding, the strategy that makes blue whales possible, has no land equivalent. There is no way to sweep up large volumes of food passively from air or soil. Energy on land is locked into discrete units that must be processed individually. This favours smaller, more agile bodies. Reproduction on land becomes riskier at large size as well. Pregnancy adds weight that must be supported against gravity. Birth involves navigating narrow passages under load. Injuries during reproduction are more likely and more severe. Recovery is slower. Water alleviates many of these issues by supporting mass during gestation and birth. On land, there is no such assistance. The cost of reproduction rises sharply with size. Land also intensifies the consequences of injury. Falls are more dangerous. Collisions are harsher. Healing is complicated by constant weight bearing. An injured limb may never fully recover. For large animals, even minor injuries can become fatal over time. All of these factors combine to create a hard ceiling. Land does not just discourage extreme size, it actively selects against it. Any lineage that pushes too far finds itself burdened by costs that cannot be offset by corresponding benefits. This is why large land animals are rare, and why those that do exist occupy narrow ecological niches. They move slowly, they reproduce infrequently, they rely on stable environments, they are vulnerable to change. The ocean, by contrast, absorbs many of these costs and redistributes them. It does not eliminate limits, but it lowers them just enough to make a different outcome possible. The blue whale is often compared to dinosaurs, but this comparison obscures a crucial point. Dinosaurs were fighting gravity at full strength. Whales are not. The ocean shares the load. That single difference cascades into every other aspect of biology. If you were to imagine placing a blue whale on land, even briefly, the problems would compound immediately. Bones would experience compressive forces they were never meant to bear. Muscles would fatigue trying to stabilize posture. Blood would pool. Organs would compress. Breathing would become laboured. Heat would build. There is no version of the blue whale that could adapt to land by gradual modification. The body plan is too dependent on buoyancy. The changes required would not be incremental. They would be catastrophic. This helps explain why the path toward extreme size was effectively closed on land long before whales began their ascent. The environment itself vetoed the experiment, not through sudden extinction or dramatic failure, but through relentless accumulation of costs. Land never stood a chance because it could not offer the one thing that makes extreme size manageable: continuous passive support. Without that, every system must overcompensate. Overcompensation leads to fragility. Fragility leads to failure. The story of the blue whale is therefore not just about what life can do, but where it can do it. The same genetic toolkit, operating under different physical conditions, produces radically different outcomes. This realization also reframes our understanding of size itself. Size is not an inherent trait. It is an agreement between an organism and its environment. On land, that agreement breaks down early. In the ocean, it holds a little longer. But even in the ocean, it does not hold forever. There is still a boundary beyond which size becomes unsustainable. Blue whales are not unlimited. They are exceptional, but they are also constrained. As we continue, that constraint becomes clearer. Because even in the most favourable environment, size carries a hidden cost. It creates dependence. Dependence on stability. Dependence on abundance. Dependence on a world that behaves predictably. The blue whale exists where those conditions align. But alignment is not permanence. and that fragility becomes impossible to ignore once another force enters the story, a force that does not obey the slow rhythms of evolution or ocean circulation. That force is us. Immense size gives the impression of permanence. When something is that large, that heavy, that dominant in scale, it feels as though it must be stable by default, as if sheer mass alone could anchor it against change. But for the blue whale, the opposite is true. Size does not create security. It creates dependence, and that dependence rests on a balance so delicate that even small shifts can send stress rippling through the entire system. Every advantage that comes with extreme size arrives paired with a cost. The larger the body, the more specialized its solutions must be. The more specialized those solutions become, the fewer alternatives remain. Flexibility narrows, options close, survival becomes less about reacting to change and more about hoping change does not arrive too quickly or too severely. This is the fragile balance behind immense size. The blue whale does not succeed because it is powerful. It succeeds because, for now, everything it depends on still behaves within a narrow set of tolerances. Consider feeding again, not as a strategy, but as a dependency. Blue whales rely on krill swarms that are not just present but dense. Density is not guaranteed. It is the result of specific oceanographic conditions. Currents must bring nutrients upward. Phytoplankton must bloom. Krill must reproduce successfully and aggregate in the right places. Timing matters. Location matters. Scale matters. If krill become more dispersed, feeding efficiency drops sharply. A whale cannot compensate by simply eating longer or swimming faster. The energetic math breaks down. Each feeding lunge has a cost, and if the payoff drops below a certain threshold, the whale loses energy rather than gaining it. There is no buffer here, no alternative prey of comparable abundance, no fallback strategy. Migration adds another layer of fragility. Blue whales move across entire ocean basins to track seasonal abundance. These migrations are energetically expensive, but they are necessary. Breeding and feeding grounds are often far apart. The whale's body is built around the assumption that it can make these journeys and arrive in good condition. Disrupt the migration, and the balance shifts. If feeding grounds move farther away, if ocean temperatures alter timing, if noise, shipping, or obstacles force detours, each change increases energy expenditure without increasing intake. Over time, that imbalance accumulates. Reproduction magnifies this vulnerability. Blue whales reproduce slowly. Gestation lasts about a year. Calves are born large and require substantial energy investment from the mother. Lactation is demanding. Milk production draws heavily on stored reserves. A female that enters reproduction without sufficient energy stores risks compromising both herself and her calf. This means successful reproduction depends on successful feeding in the preceding seasons. There is no margin for repeated failure. A bad year can echo forward, reducing reproductive success for years afterward. For a species with long lifespans and low birth rates, recovery from sustained stress is slow. Longevity, often seen as an advantage, also plays a role in fragility. Long-lived species tend to reproduce less frequently and invest more in each offspring. This strategy works when adult survival is high and conditions are stable. It works poorly when environments change rapidly or unpredictably. Blue whales evolved in a world where large-scale changes unfolded slowly. Ocean circulation patterns shifted over thousands or millions of years. Ecosystems adjusted gradually. Under those conditions, specialization made sense. Under modern conditions, where change can happen on the scale of decades, specialization becomes a risk. Noise pollution offers a clear example of how small disruptions can have outsized effects. Blue whales rely on sound to navigate, communicate, and potentially locate feeding areas. Low-frequency noise from ships, sonar, and industrial activity overlaps with the frequencies whales use. This noise does not injure directly, but it interferes. Interference forces behavioural changes. Whales may alter dive patterns, they may avoid certain areas, they may expend more energy communicating. Each adjustment carries a cost. Individually, these costs may seem small. Collectively, they erode the delicate balance that size depends on. Ship strikes present another asymmetry. A blue whale is massive, but ships are faster, harder, and indifferent to biological limits. A collision that a smaller animal might avoid becomes unavoidable at scale. The whale's size, once a defense against natural predators, offers no protection here. Climate change introduces deeper uncertainty. Changes in ocean temperature affect stratification, which affects nutrient mixing, which affects phytoplankton growth, which affects krill. The entire food web shifts. These shifts do not need to eliminate krill entirely to cause problems. A change in timing or distribution is enough. If peak krill abundance occurs earlier or later than usual, whales arriving on historical schedules may miss optimal feeding windows. If krill move deeper or disperse over larger areas, feeding efficiency declines. The whale cannot adapt quickly. Its behaviour is tuned to patterns that evolved over long time scales. Even the physical properties of water are part of this balance. Temperature affects density. Density affects buoyancy. Buoyancy affects energy expenditure. Small changes ripple outward. A slightly warmer ocean may require whales to expend more effort, maintaining position or diving, increasing baseline energy costs. The fragility extends inward as well. A body operating near physiological limits has little room to absorb stress. Illness, injury, or chronic disturbance can push systems past thresholds. Healing takes time. Recovery requires energy. Both are constrained. This is why blue whales are paradoxically vulnerable despite their size. They're not adaptable generalists. They're finely tuned specialists. Their success depends on the continued existence of a particular set of conditions that favour their strategy. Contrast this with smaller animals, which often survive precisely because they can shift strategies. They can switch prey, alter habitats, reproduce quickly, evolve faster. Size buys resilience only up to a point. Beyond that point, it buys efficiency at the cost of flexibility. The blue whale crossed that point long ago. It did so because efficiency was rewarded strongly enough to outweigh the risks. But the risks never disappeared. They were merely postponed. This balance also explains why there are so few blue whales relative to their size. Population density is low. Individuals are spread out across vast areas. This reduces competition and allows sufficient food for each whale, but it also means encounters are rare. Social structures are loose. Mating opportunities depend on successful navigation and timing. Low population density also slows recovery from decline. When numbers drop, finding mates becomes harder. Genetic diversity can decrease. Local disruptions can have lasting effects. Large size does not protect against these dynamics, it amplifies them. Everything about the blue whale's existence points to narrow margins. Energy margins, reproductive margins, ecological margins, physical margins. It survives not because those margins are wide, but because until recently they were stable. This perspective changes how size should be interpreted. The blue whale is not an example of nature's excess. It is an example of nature's precision, a solution that works only when many variables remain aligned. This precision is easy to miss when looking at a single animal gliding calmly through the water. It appears effortless, but that effortlessness is the result of continuous balance, maintained moment by moment. The fragile balance behind immense size also explains why such size has evolved so rarely. It is not enough for conditions to be good. They must be good in very specific ways, and they must remain that way for long enough for evolutionary processes to take advantage. This rarity makes the blue whale both remarkable and precarious. It represents the furthest reach of a particular strategy, not a general rule. It shows how far life can stretch under the right circumstances, but also how little room there is at the edge. As this balance becomes more strained, the consequences are not immediate collapse but gradual erosion. Slightly reduced feeding success, slightly longer migrations, slightly higher energy costs. Over time, these shifts accumulate. Understanding this fragility is essential for understanding why blue whales should not exist and why they do anyway. They exist because, for a long time, the balance held, and they continue to exist because for now it mostly still does. But the presence of such a narrow balance raises an unavoidable question. What happens when a new force enters the system, one that operates faster than climate cycles, faster than evolutionary adjustment, and with little regard for existing constraints? That question leads directly into the next part of the story, where the ancient negotiation between size and environment encounters a new variable, one that did not evolve alongside the whale, and one that alters the balance in ways the whale's body was never designed to absorb. For most of their existence, blue whales lived in a world that changed slowly. Ocean currents shifted over millennia. Climate cycles unfolded over thousands of years. Predator pressures rose and fell gradually. Even major ecological reorganizations gave evolution time to respond. The fragile balance that allowed extreme size was tested repeatedly, but never suddenly. That changed when humans entered the ocean as a dominant force. At first, the interaction was incidental. Early humans encountered whales rarely. A stranded whale was an event, not a resource. Coastal cultures learned to take advantage of beached animals, harvesting meat and blubber when opportunity presented itself, but they did not shape whale populations in any systematic way. For a long time, blue whales remained far beyond human reach, protected by distance, scale, and the simple difficulty of finding them. This protection did not last. The shift came not through intent, but through technology. As ships grew larger and more capable, humans began to move through the open ocean more regularly. Navigation improved, harpoons evolved, engines replaced sails. Suddenly, the vastness that once sheltered blue whales became traversable, and size, once a defense, became a liability. Industrial whaling did not target blue whales first. Earlier whalers pursued species that were easier to catch and process. But as those populations declined, attention turned to larger and faster whales. Steam-powered ships could keep pace. Explosive harpoons could penetrate thick blubber. Winches could haul bodies that would have been unmanageable before. Blue whales, with their enormous size and high yield of oil, became valuable targets. Their blubber could be rendered into vast quantities of oil. Their bodies represented efficiency from a human perspective, even as they represented fragility from a biological one. The impact was swift and disproportionate. In a matter of decades, populations that had persisted for millions of years were reduced to a fraction of their former numbers. This was not predation in any evolutionary sense. It was extraction. Removal at a rate far beyond what slow reproduction could replace. What makes this moment especially significant is how completely it bypassed the whale's defences. Size offered no protection. Longevity offered no advantage. Specialisation offered no escape. The traits that made blue whales successful in their environment were irrelevant in the face of industrial-scale hunting. Even after commercial whaling was curtailed and eventually banned, the balance did not simply reset. Recovery has been slow. Blue whales reproduce infrequently. Calves take years to mature. Populations increase gradually even under ideal conditions. Decades after protection, many populations remain well below historical levels. But hunting was only the first way humans altered the system. As whaling declined, other pressures took its place, quieter but persistent. Modern shipping introduced a new kind of hazard. The open ocean, once relatively empty of fast-moving obstacles, became a network of shipping lanes. Large vessels move quickly and predictably, but not in ways whales evolved to anticipate. Blue whales are not agile. Their reaction times and turning radii are constrained by size. Avoiding a ship is often impossible once it is close. Ship strikes do not need to be frequent to matter. When populations are small and reproduction is slow, the loss of even a few individuals per year can slow or reverse recovery. Again, size offers no protection. In fact, it increases risk by making whales more likely to intersect shipping routes near the surface. Noise adds another layer of disruption. The ocean was never silent, but the sounds it carried were mostly biological or geological. Waves, storms, earthquakes, whale calls. Human-generated noise, especially at low frequencies, occupies the same acoustic space blue whales use to communicate. This noise does not have to be loud in a human sense to be disruptive. It only needs to overlap in frequency and persist long enough to interfere. Communication range shrinks, signals are masked. Whales may need to call louder or more often, expending additional energy. They may fail to locate mates or coordinate movement effectively. Navigation may also be affected. While the details are still being studied, it is clear that sound plays a role in how whales perceive their environment. Altering the acoustic landscape changes how that environment can be read. Then there is the most pervasive influence of all: climate change. Rising ocean temperatures alter stratification. Stratification affects nutrient mixing. Nutrient mixing affects phytoplankton. Phytoplankton affects krill. Each link in this chain is sensitive to temperature, timing, and chemistry. Small changes at the base can cascade upward, reaching the largest animals in the system. For blue whales, this manifests not as sudden starvation, but as subtle shifts. Krill swarms may form in different places. Peak abundance may occur earlier or later. Prey may concentrate at different depths. Each shift forces behavioral adjustments. Behavioral adjustments cost energy. Energy margins are already narrow. Over time, repeated small increases in cost without corresponding. Increases in intake can erode the balance that size depends on. Chemical changes matter too. Ocean acidification affects plankton communities. Changes in ice cover alter seasonal productivity. Altered currents reshape migration corridors. None of these changes target blue whales specifically, but all of them reshape the environment that made blue whales possible. What makes human influence distinct from earlier environmental changes is speed. Evolution cannot keep up with rapid shifts occurring over decades. Blue whales cannot quickly change their feeding strategy, migration routes, or reproductive timing. Their bodies and behaviours are tuned to patterns that were stable for thousands of years. This mismatch between the pace of change and the pace of adaptation is the core of the problem. The blue whale's size evolved under conditions of slow change. Human influence compresses that change into a time frame too short for adjustment. Even conservation efforts, while essential, operate within this constraint. Protecting individuals from hunting is necessary, but it does not restore historical ocean conditions. Reducing ship strikes helps, but it does not address shifting prey distributions. Mitigating noise helps, but it does not remove it entirely. The presence of humans has transformed the ocean from a mostly self-regulating system into one shaped by external priorities. Shipping, fishing, resource extraction, and climate forcing all operate on human timescales and human needs, not biological ones. For a species whose survival depends on fine balance, this introduces persistent instability. The whale's size, once a solution, becomes a sensitivity. The bigger the body, the more it depends on predictable conditions. The more specialized the strategy, the harder it is to adapt. Yet it is important to note that blue whales have not disappeared. Despite everything, they persist. They migrate. They feed. They reproduce. Slowly, in some regions, numbers increase. This persistence speaks to the resilience built into their design, but also to how close the system still is to functioning. Their continued existence is not guaranteed, but it is not accidental either. It depends on whether the balance they rely on can be maintained well enough, long enough, for them to continue doing what they have always done. When humans enter the story, the narrative shifts from one of slow natural negotiation to one of rapid intervention. The question is no longer just whether size is possible, but whether it can be sustained in a world changing faster than the rules that allowed it to emerge. This leads naturally to the next consideration. If blue whales exist at the edge of possibility, and if human influence has narrowed that edge, then their rarity is not surprising. It is inevitable. Understanding why they are so few, and why they always will be, requires looking at size not as a triumph, but as a constraint that limits how many individuals a system can support at once. Rarity is not a flaw in the blue whale's story. It is the inevitable outcome of everything that makes the blue whale possible in the first place. Extreme size does not scale toward abundance, it scales toward scarcity. The same forces that allow a body to grow so large also ensure that very few such bodies can exist at the same time. At the most basic level, this is an issue of energy. The ocean produces a vast amount of biomass, but it does not produce it evenly. Energy is captured by phytoplankton in thin layers near the surface, then passed upward through the food web with losses at every step. By the time energy reaches krill, and then the animals that feed on krill, only a small fraction of the original input remains. Blue whales sit at the top of this chain. Each individual represents an enormous concentration of energy. Supporting even one requires vast feeding grounds and dense prey. Supporting many requires those conditions to exist repeatedly, across large regions, year after year. There is a limit to how many blue whales a given ocean can support. That limit is low, not because the ocean is poor, but because the whales are expensive. One whale can consume several tons of krill per day during feeding seasons. Multiply that by thousands of individuals, and the demand becomes immense. This does not mean the ocean could not support more whales under any circumstances. It means that supporting more whales would require prey densities and productivity levels that are rarely sustained over large areas. The system favours a small number of very large consumers rather than a large number of them. Rarity is reinforced by reproduction. Blue whales reproduce slowly. Females do not give birth frequently. Calves take years to mature. Each new individual represents a long-term investment of energy and time. Population growth, even under ideal conditions, is gradual. This slow pace is not a weakness in stable environments. It reduces competition. It allows individuals to live long lives. It aligns with a strategy where survival is prioritized over rapid replacement. But it also means recovery from decline is slow, and expansion beyond a certain point is unlikely. Large size also demands large space. Blue whales do not live in dense social groups. They are spread out across ocean basins. This spacing is not accidental. It reflects the distribution of resources. Clustering would lead to competition and reduced feeding efficiency. As a result, encounters between individuals are relatively infrequent. Mating depends on timing and movement rather than constant proximity. This further limits population density. The ocean may be vast, but usable habitat for blue whales, defined by suitable preying conditions, is much smaller. There is also the matter of specialization. Blue whales feed almost exclusively on krill. They do not switch easily to other prey. This specialization locks them into a narrow ecological role. If krill populations decline or shift, blue whales cannot compensate by diversifying their diet. Specialization often increases efficiency, but it reduces resilience. It ties a species' fate to the stability of a particular resource. This trade-off is acceptable only when that resource is reliable over long timescales. When it is not, rarity becomes more pronounced. Size itself limits reproductive strategies. Blue whales cannot produce many offspring quickly. Gestation is long. Calves are large and energetically costly. Parenting requires sustained investment. These constraints cap population growth even when conditions are favourable. Predation pressure on adult blue whales is minimal. but this does not lead to population explosion. The limiting factors are not mortality from predators, but energy availability and reproductive pace. Removing predators does not increase numbers if food remains the bottleneck. Another factor is evolutionary inertia. Blue whales are not rapidly evolving organisms. Their long generation times slow genetic change. This means that adaptation to new conditions happens gradually, if at all. They are built to persist, not to pivot. All of this means that blue whales were never numerous, even before human intervention. Historical estimates suggest populations were larger than today, but still sparse relative to smaller marine species. Their presence was always defined by low density and wide distribution. This rarity has implications beyond numbers. It affects social structure, genetic diversity, and vulnerability to disturbance. Small populations spread thinly across large areas are harder to monitor and protect. Local declines may go unnoticed for years. Rarity also affects how blue whales interact with their environment. Their ecological impact is significant, but diffuse. They influence nutrient cycling and ecosystem structure over large scales, but no single area depends exclusively on them. This makes their absence less immediately obvious, even as it alters systems over time. The phrase, "and always will be," is not a statement of doom. It is a recognition of constraints. Even in a perfectly protected ocean, blue whales would remain rare. Their biology does not allow for abundance. This perspective helps clarify conservation goals. The aim is not to create oceans filled with blue whales. That would be neither realistic nor ecologically appropriate. The aim is to maintain conditions that allow blue whales to exist at all. Their rarity is part of their identity. It is the price of being so large. It is the outcome of energy economics, reproductive strategy, and environmental specialization intersecting at extreme scale. Understanding this removes a common misconception. Blue whales are not rare because they are failing. They are rare because they are optimized for a niche that does not support high numbers. They are not declining by default. They are constrained by design. This also reframes how we think about success in evolution. Success is not measured by abundance alone. It can also be measured by persistence, by the ability to maintain a particular form over long periods under stable conditions. Blue whales represent success in this sense. They have maintained extreme size for millions of years. They have survived climate shifts, ocean reorganizations, and ecological turnovers. Their rarity did not prevent them from enduring, but rarity does mean vulnerability. When numbers are low, margins are thin. There is less capacity to absorb losses, less redundancy, less buffering against change. This is why modern pressures matter so much. When populations are already sparse, additional mortality or reduced reproduction can have outsized effects. Recovery becomes slower. The balance becomes harder to maintain. The blue whale's existence is therefore a quiet paradox. It is the largest animal ever to live, yet it occupies the ocean lightly. It does not dominate by numbers or force. It persists through efficiency and restraint. As we approach the end of this exploration, this paradox becomes central. The blue whale should not exist because the constraints are severe, the margins narrow, and the dependencies many. And yet it does exist, because for a time, and for now, the conditions align just enough. What remains is not a conclusion in the traditional sense, but a reflection on what this existence tells us about life itself, about limits, about possibility, and about what it means to encounter something that lives so close to the edge of what the world allows. It is tempting to end a story like this with a sense of resolution, to gather the threads, tie them neatly together, and step back with the feeling that the question has been answered. But the blue whale does not invite that kind of ending. Its existence resists neat conclusions in the same way it resists simple explanations. It is not a solved problem. It is an ongoing condition. The blue whale swims today not because the universe guaranteed it a place, but because moment by moment the balance still holds. The ocean still lifts its weight. Krill still gather densely enough, often enough. Its heart still keeps time. Its lungs still refill. Its migration still leads somewhere worth arriving at. None of this is automatic. None of it is permanent. Calling the blue whale a miracle does not mean invoking anything supernatural. It means recognizing that something exists where the odds against it are unusually high. It means acknowledging that the laws of physics, biology, and ecology all impose constraints that normally prevent life from reaching this scale, and that in this one case, those constraints were bent just enough, in just the right configuration to allow it. What makes this miracle different from others is how quietly it persists. Blue whales do not announce themselves often. They do not dominate coastlines. They do not reshape landscapes in obvious ways. Most people will never see one in their lifetime. Many will live their entire lives without ever thinking about them in detail. And yet, somewhere far from shore, a body heavier than any animal that has ever lived is moving through water with slow, deliberate strokes. It is breathing. It is feeding. It is responding to the same forces that shape everything else on this planet, only at a scale that makes those forces visible in a new way. The miracle is not just that the blue whale exists, but that it exists without spectacle. It does not roar. It does not display aggression. It does not build monuments or leave traces on land. It moves, eats, rests, and migrates, largely unnoticed, as it has for millions of years. In a sense, the blue whale is not an exception to the rules of nature. It is a demonstration of them. It shows what happens when energy, environment, and evolution align closely enough to allow something extreme without collapsing the system. It shows how narrow that alignment is. Everything about the blue whale's life reflects restraint. Its movements are measured. Its feeding is selective. Its reproduction is slow. Its population is sparse. There is no excess anywhere in the design. Every system is sized for just enough. That just enough is what makes the miracle fragile. It does not tolerate much deviation. There is no large buffer waiting to absorb mistakes. When conditions worsen, the response is not explosive collapse but gradual erosion. Feeding becomes slightly less efficient. Migrations become slightly more costly. Recovery becomes slightly slower. These changes are easy to overlook because they are subtle. The whale still swims, still feeds, still appears calm at the surface. But the balance shifts quietly, the way it always has, only now the shifts are faster and less predictable. This is where the story remains unfinished. The blue whale is not a relic of the past. It is not a completed chapter in natural history. It is a living experiment that continues to run, subject to variables that are still changing. When people ask whether blue whales will survive, the question often sounds dramatic, as if extinction would arrive suddenly, like a door slamming shut. In reality, the answer lies in gradients, in probabilities, in how often feeding succeeds, in how many calves survive, in whether the balance holds well enough, long enough. The miracle that still swims is not defined by certainty. It is defined by persistence in the face of constraint. There is something humbling about that. The blue whale does not conquer its environment. It depends on it completely. It does not overpower physics. It negotiates with it. It does not dominate the ocean. It requires the ocean to behave in specific ways over and over again. In that sense, the blue whale is not separate from the world it lives in. It is a measure of that world's capacity. When the ocean can support a blue whale, it says something about the state of the system as a whole. When it struggles to do so, that too is a signal. This is why the blue whale often feels symbolic, even when we avoid metaphor. It sits at the far edge of what biology can assemble, not as a goal, but as a boundary marker. It shows where life stops scaling up and starts failing. But boundaries are not static. They move as conditions change. The existence of the blue whale tells us that the boundary once moved outward, just far enough to allow something extraordinary. Whether it remains there is an open question. None of this requires drama to matter. It matters precisely because it unfolds quietly, because it happens far from daily human experience, because it does not announce itself with urgency. A blue whale surfacing is not a crisis. It is a breath, a pause, a release of air that carries decades of evolutionary history and a vast amount of biological investment into a single, visible moment. Then it slips back beneath the surface and the ocean closes over it as if nothing happened. But something did happen. The balance held once again. If there's any lesson here, it is not about size as achievement. It is about limits as context. The blue whale is not impressive because it is large. It is impressive because it exists where it almost cannot. It reminds us that life does not expand indefinitely toward grandeur. It explores what is permitted, and when permission is granted, even briefly, life moves into that space and occupies it as fully as it can. The blue whale occupies that space with restraint, efficiency, and vulnerability. It does not leave room for many others to join it there. That is why it is rare. That is why it always will be. And still, it swims. Somewhere right now, far from where you're listening, a blue whale is moving through cold, dark water. It is not aware of its status as the largest animal that ever lived. It is not aware of the improbability of its existence. It is responding to pressure, to sound, to hunger, to instinct, the same way any living thing does. The miracle is not that it knows what it is. The miracle is that the world still knows how to hold it. And for as long as that remains true, the blue whale will continue to do what it has always done, not proving anything, not reaching for anything, simply existing at the very edge of what the planet allows, one slow, deliberate movement at a time,